There was a time when strange oceans swallowed entire continents, when the skies were ruled by dragon-sized insects, and when towering volcanoes reshaped the land in the blink of an eye. This was a prehistoric Earth. Between 500 and 66 million years ago, our planet was a shifting canvas of evolution and chaos. Giant trilobites scuttled across the seafloor long before the first dinosaur ever roared. Supercontinents like Gondwana and Pangaea formed and split apart in slow-motion continental collisions. Lush fern jungles once covered polar regions, and deserts bloomed where oceans had drowned the land. Every era brought new life forms, some bizarre, some beautiful, many destined for extinction. Before we begin this prehistoric ride, let us know where in the world you're watching from and what time it is for you right now. Drop it in the comments below and settle in for a fascinating journey. The Cambrian period was the very first chapter of the Paleozoic era and a major part of the Phanerozoic eon, the era in Earth's history when life truly began to flourish in visible and complex ways. This period lasted for about 51.95 million years, starting around 538.8 million years ago and ending around 486.85 million years ago, when the Ordovician period began. Back then, Earth looked very different. Most of the land masses were grouped in the southern half of the planet and surrounded by an enormous ocean called Panthalassa. Meanwhile, a huge supercontinent called Gondwana was coming together as its pieces collided and fused during the Ediacaran and early Cambrian times. The movement of Earth's plates created new mountain building zones and volcanic activity along the edges. These changes helped raise global temperatures. At the same time, another landmass named Laurentia sat along the equator, separated from Gondwana by the widening Iapetus Ocean. But the most remarkable thing about the Cambrian was what happened to life itself. Before this period, most living things were tiny single-celled creatures, and their fossils are extremely rare. Some complex, multicellular organisms had started to appear toward the end of the Ediacaran, but during the Cambrian, something extraordinary occurred. The Cambrian explosion. This was a sudden burst in the variety and complexity of life, giving rise to the first members of nearly all major animal groups we know today. What also makes the Cambrian stand out is its many Lagerstätten, special fossil sites, where not just hard shells, but even the soft parts of organisms were preserved. These deposits give us rare and precious snapshots of early life in exceptional detail. The word Cambrian comes from the Latin version of the Welsh name for Wales, Cymru. It was in Wales that rocks from this time period were first seriously studied. In the year 1835, geologist Adam Sedgwick gave the Cambrian its name and divided it into three parts: lower, middle, and upper. He worked with fellow geologist Roderick Murchison to draw the boundary between the Cambrian and the overlying Silurian layers. At first, they agreed, but this agreement did not last. Because early Cambrian rocks didn't have many fossils, Sedgwick relied on the types of rock to define his Cambrian layers. Meanwhile, Murchison found more fossils in Silurian rocks and used these to make connections across Europe and Russia. As scientists began to find fossils in older rocks, Murchison pushed the Silurian boundary downward into territory Sedgwick claimed as Cambrian. This led to a scientific tug-of-war between their camps. Things got more complicated in the year 1852, when new fieldwork showed a clear break, or unconformity, within the Silurian rocks. This difference in fossil types allowed Sedgwick to reclaim some of that territory for the Cambrian. Still, the disagreement continued long after both men had died. Finally, in the year 1879, geologist Charles Lapworth stepped in. He proposed that the disputed layers belonged to a new period altogether, which he called the Ordovician. The term Cambrian was formally accepted in 1960 at the 21st International Geological Congress. It now only includes what Sedgwick originally called the Lower Cambrian, though it reaches into even older rocks today. To make global comparisons, geologists use a system called the Global Boundary Stratotype Section and Point, or GSSP. These are specific locations around the world where the start of a geological time unit is clearly recorded in rock layers. The Cambrian period is now divided into 4 major segments called series and 10 smaller divisions called stages. At first, scientists thought the Cambrian began when trilobites, the ancient armored ancestors of modern arthropods, first appeared. However, they later discovered small shell fossils and Ediacaran organisms that came even earlier. This led to the need for a more precise starting point for the Cambrian. It wasn't until 1994 that the Cambrian period was officially defined. Scientists chose a site called Fortune Head in Newfoundland, Canada. The base of the Cambrian there is marked by the appearance of a fossil named Treptichnus pedum, a type of burrow that represents more complex animal behavior. Early estimates dated the beginning of the Cambrian to about 570 million years ago, but newer and more accurate dating methods now place it at 538.8 million years ago, with a margin of error of about plus or minus 0.6 million years. This date comes from ash layers in Oman, which also show a drop in carbon-13 levels and the disappearance of signature Ediacaran life. However, some researchers argue that this site may not mark the true boundary and prefer slightly older estimates of 544 to 542 million years ago. In Russia, many paleontologists prefer to set the Cambrian's beginning at the start of the Timoshan stage, marked by the rise of mineral skeletons and the first archaeocyanid reefs. There were 4 parts of the Cambrian period. The Tiranuvian series, dated to about 538.8 to 521 million years ago. This is the earliest chapter of the Cambrian. It contains no trilobite fossils. It includes the Fortunian stage and an unnamed stage, 2 characterized by trace fossils and small shell fossils. The name Tiranuvian was made official in the year 2007. The Cambrian Series 2, about 521 to 506.5 million years ago, is not yet officially named. It includes Cambrian Stage 3 and Stage 4. This period saw a burst in animal diversity, especially in trilobites and archaeocyands. Global comparisons are hard due to regional differences in fossils. The Meolingian series, about 506.5 to 497 million years ago, formerly called Cambrian Series 3. It includes the Woollian, Drumian, and Gujangian stages. It was approved in 2018 and is named after the Meoling Mountains in China. This period begins with the appearance of the trilobite Eryctocephalus indicus at the boundary between Series 2 and the Meolingian. Many trilobite types, like the Olenellids, Eodicids, and Redlichids, went extinct. This is considered the first known mass extinction of trilobites. The Ferrongian series, about 497 to 486.85 million years ago. This is the final segment of the Cambrian. The name was approved in 2003 and replaced the older term, Upper Cambrian. It begins with the appearance of the trilobite Glyptognostus reticulatus. It includes the Pabian stage, the Jiangshanian stage, and an unnamed stage 10. The Cambrian Ordovician boundary is officially marked at Green Point in western Newfoundland, Canada, and dated to 486.85 million years ago. This point is defined by the appearance of a tiny tooth-like fossil Hirsutodontus simplex. In areas where this fossil isn't found, scientists use other markers, such as planktonic graptolites or the trilobite Geoespedella borealis. Several major meteorites struck Earth during the Cambrian around 535 million years ago. A large impact created the Nogrund crater in Estonia, which is about 20 kilometers wide. The Gardnose crater in Norway, about 5 kilometers wide, formed around 500 million years ago in a shallow sea. During the Cambrian period, the Earth's climate was mostly warm and humid. Scientists know this because of the kinds of sediments and rock formations found from that time. These include tropical carbonate platforms, reefs built by ancient sponge-like creatures called archaeocyanths, deposits of bauxite, which forms in warm, wet climates, and minerals like evaporites and calcretes that are typical of dry, arid zones. The widespread of these features, especially in tropical areas, stretching across many latitudes, tells us that the Earth was in what scientists call a greenhouse climate, a time when there were no major ice sheets, and temperatures were consistently high across much of the planet. Toward the end of the Cambrian, fossil evidence from trilobites, extinct marine creatures with hard shells, suggests that there was only a gentle temperature difference between the poles and the equator. In other words, even the polar regions weren't extremely cold, showing how evenly warm the Earth was. Some scientists have found signs of ancient glaciers in the Avalonia region, which was located in high southern latitudes at the time, but there's still debate about whether those icy sediments were actually formed in the Cambrian or in the slightly earlier Neoproterozoic period. When it comes to measuring how hot the Earth really was during the Cambrian, the results vary depending on the method used. Some estimates suggest that the global average temperature may have been over 40 degrees Celsius or 104 degrees Fahrenheit. However, more reliable models that pull information from multiple sources give more moderate temperatures, around 20 to 22 degrees Celsius, at the very beginning of the Cambrian, rising to about 23 to 25 degrees Celsius for the rest of the period. This long-lasting warmth was strongly tied to high levels of carbon dioxide in the atmosphere. A major factor in this was the assembly of the massive supercontinent Gondwana. As land masses came together, Earth's tectonic plates shifted and formed new boundaries where volcanic activity occurred. These volcanic eruptions released large amounts of greenhouse gases, like carbon dioxide, which further warmed the planet. In particular, a huge volcanic event, known as the Kalkarinji Large Igneous Province, erupted around stage 4 of the Cambrian and continued into the early Meolingian. These eruptions poured enormous quantities of carbon dioxide, methane, and sulfur dioxide into the air, causing sudden changes in climate and raising sea surface temperatures significantly. However, there is still a lot of uncertainty about exactly how hot the oceans became. Scientists try to figure this out by studying oxygen isotope levels in ancient marine rocks, but there's ongoing debate over what those values really mean when comparing Cambrian oceans to other times in Earth's history. Depending on which estimates you look at, tropical sea surface temperatures during the Cambrian may have ranged from 28 to 32 degrees Celsius, or even from 29 to 38 degrees Celsius. By comparison, today's average tropical sea surface temperature is around 26 degrees Celsius. While temperatures soared, atmospheric oxygen levels were still quite low compared to today. Oxygen had been rising steadily since the Neoproterozoic period, thanks to the growth of photosynthesizing organisms in the oceans. But during the Cambrian, oxygen levels in the atmosphere fluctuated between about 3% and 14%, far below the modern level of about 21%. The combination of low oxygen in the air and high temperatures in the oceans meant that less oxygen could dissolve in seawater, especially in deeper regions. This led to anoxic conditions, where deep parts of the ocean were almost entirely lacking in oxygen. These low oxygen environments had a big impact on marine life and the evolution of early animals. As new kinds of organisms began to burrow into ocean sediments, they mixed up the layers of mud and exposed deeper oxygen-poor materials to the oxygen-rich waters above. This process, known as bioturbation, actually reduced the burial of organic carbon and sulfur in the sediments. Over time, this made it harder for oxygen to build up in the atmosphere and oceans, contributing to more widespread oxygen shortages underwater. On the other hand, when the continents experienced high rates of weathering, the breakdown of rocks due to wind, rain, and other natural forces, more nutrients flowed into the oceans. This sudden burst of nutrients led to a bloom in phytoplankton, tiny photosynthetic organisms that form the base of the food chain. Their explosion in numbers helped fuel the evolution of more complex animal life. But when these plankton blooms happen too quickly, they cause eutrophication, a process where too much organic matter is produced and later decomposes, consuming oxygen and leaving water severely depleted of it. These cycles of rising and falling oxygen levels shaped life on Earth in powerful ways. Whenever oxygen levels rose, Biodiversity increased, more oxygen supported, more active lifestyles, bigger body sizes, and more complex ecosystems, as oxygen-rich conditions expanded the habitable seafloor. But when oxygen levels dropped, due to changes in sea level, shifts in ocean currents, or upwelling of deeper low-oxygen waters, many animals could not survive. These low-oxygen events led to mass extinctions, sometimes in specific regions, and other times across the globe. All in all, the Cambrian period was a time of dramatic environmental ups and downs. These swings between oxygen-rich and oxygen-poor conditions played a major role in driving evolutionary innovation, causing some species to go extinct and pushing others to adapt in new and remarkable ways. As for plant life, there wasn't much on land during the Cambrian. The plants of the sea didn't look very different from those that existed just before during the Ediacaran period. The main types were large algae, including forms named Fucinospira, Cinocylindra, and Marpolia. Interestingly, no calcareous or calcium carbonate containing algae have been found from this time. There are no fossils of land plants, what scientists call embryophytes, from the Cambrian. However, microbial life thrived on land, especially in the form of biofilms and microbial mats that covered tidal flats and beaches as early as 500 million years ago. These microbial communities played a role similar to modern-day soil crusts in deserts, helping stabilize the ground and contributing to the early formation of soils. Although some molecular clock studies suggest that land plants may have first evolved during the Middle or Late Cambrian, this idea remains controversial. What is clearer is that the large-scale removal of atmospheric carbon dioxide by these plants through a process called carbon sequestration didn't truly begin until the Ordovician period, which followed the Cambrian. Some researchers also think that arthropods, creatures like insects and spiders, may have started to move onto land during the Cambrian based on genetic evidence. But like land plants, the oldest definite fossils of land arthropods also appear in the Ordovician, making their Cambrian origin uncertain and still a topic of debate. The Cambrian explosion was a time of extraordinary change and growth in the history of life on Earth. It happened roughly 541 million years ago, marking the beginning of a new chapter, when life became more complex and diverse. During this period, many different types of animals developed rapidly, especially those with more than one cell, what we call multicellular life. Most creatures that lived during the Cambrian period lived in the ocean. For a long time, scientists believed that trilobites, a kind of ancient sea creature with a hard shell, were the most common animals of the time. But newer research has shown this wasn't exactly true. Trilobites were certainly important, but they were only one part of a much larger group called arthropods, a group that includes insects, crabs, spiders, and others. In the Cambrian seas, arthropods were the real rulers, but many of them had soft, fragile bodies that didn't fossilize easily. Trilobites, on the other hand, had strong armor-like shells made of calcium carbonate, a substance similar to what makes up seashells. These shells preserved well in the fossil record, making trilobites seem far more common than they actually were. This period marked a turning point for life on Earth. A dramatic increase in the number and types of species occurred, but not all life forms made it through this transition. The Ediacaran biota, soft-bodied organisms that lived before the Cambrian, suffered a mass extinction. Around the same time, new animal behaviors appeared, especially burrowing into the seafloor. These burrowing creatures changed the ocean floor in ways that could not be undone. Before this, the seafloor was mostly covered by thick microbial mats, like slimy blankets of microorganisms. But as animals dug through the seabed, they disrupted and eventually destroyed many of these mats in a process called bioturbation. This forced the creatures that relied on the mats either to adapt or die out. Those that could adjust began to take advantage of the new types of habitats that formed in the disturbed seabed. During the same period, animals with hard mineralized body parts, such as shells, began to appear more frequently. These included representatives from most of the major groups, or phyla, of animals that we still recognize today. One example is the bryozoans, tiny colonial creatures that were once thought to have appeared much later in the Ordovician period. but most of these early animals were only primitive ancestors of today's forms. And since animals with mineralized bodies usually lived on the seafloor, they didn't fully represent the diversity of soft-bodied life that may have been far more abundant. Even though the early Cambrian period was a time of incredible growth, earning it the name Cambrian explosion, this boom didn't last forever. Around 515 million years ago, things began to change. The number of species going extinct started to outpace the number of new species appearing. About 5 million years later, the total number of different genera, a way of grouping related species, dropped from around 600 to just 450. The rate at which new species were forming fell to as little as 1/5 or 1/3 of what it had been earlier. By around 500 million years ago, oxygen levels in the oceans dropped sharply. This caused hypoxia, a situation where there isn't enough oxygen for most animals to survive. At the same time, levels of hydrogen sulfide, a toxic gas, began to rise, a dangerous combination that led to yet another extinction event. The second half of the Cambrian period turned out to be much quieter and less biologically rich than the first. Several quick waves of extinction occurred. Reef-building sponges, called archaeocyaths, which had taken over from older reef-forming organisms like stromatolites, eventually died out too. After their disappearance, stromatolites made a brief comeback, but overall biodiversity remained low until the Great Ordovician biodiversification event, which brought another explosion of life later on. Life in the Cambrian oceans wasn't easy. Oxygen levels were often low and unpredictable. When deep ocean waters that lacked oxygen occasionally rose up into shallower areas, a process known as upwelling, entire communities of organisms could be wiped out. Yet, these stresses also pushed evolution forward, eventually leading to greater biodiversity. Interestingly, some Cambrian animals even started to explore the land. Fossils of their movement, known as trace fossils, have been found. Two of these are called protognites and climactonites. Scientists believe that at least some of the protognites were made by an extinct type of arthropod called a euthocarcinoid. As for climactonites, no fossils of the creature that made them have been discovered yet, but the tracks and resting marks they left behind suggest a large, soft-bodied creature, possibly something like a giant slug or an early mollusk. Compared to later periods in Earth's history, the variety of animals during the Cambrian was still quite limited. Creatures that floated freely in the water were rare. Most animals lived on or just above the seafloor. Animals with mineralized shells or skeletons were also less common than they would become in later periods. One reason for this was the chemistry of the ocean, which wasn't ideal for forming and preserving hard parts. Despite these limitations, the Cambrian period gave us some of the most remarkable fossil discoveries ever found. Many fossils from this time preserved not just bones or shells, but also soft tissues, like skin, gills, and digestive systems, things that rarely survive in the fossil record. These special fossil sites, known as Lagerstätten, give us an extraordinary window into ancient life. Some of the most famous examples include Sirius Passet in Greenland, the Sinsk algal beds in Russia, the Manotian shales in China, the Emu Bay Shale in Australia, and the Burgess Shale in Canada. These incredible fossil beds, filled with the bizarre and beautiful creatures of the Cambrian, offer a glimpse of what was to come as life continued its march forward into the next great chapter of Earth's story, the Ordovician period. The Ordovician period was the second chapter of the Paleozoic era. It began around 486.85 million years ago at the end of the Cambrian period and lasted for about 44.5 million years, ending around 443.8 million years ago. This was a time of immense change, both for life on Earth and for the planet itself. The period is named after the Ordovices, an ancient Celtic tribe that once lived in a region of Wales where geologist Charles Lapworth first studied the distinctive rock layers of this era in the year 1879. During the Ordovician, the continents were still very different from today. The huge supercontinent, Gondwana, was the dominant landmass in the southern hemisphere, gradually drifting toward the South Pole. Meanwhile, Laurentia, a continent that included most of modern North America, remained near the equator. A number of smaller continents, including Baltica, Scandinavia, and Eastern Europe, Avalonia, New England, parts of eastern Canada, and the British Isles, and Siberia, were also scattered across the globe. The most important geological event of this period was the slow collision of Baltica and Laurentia, a process that would lead to the formation of a new continent called Euramerica. The Ordovician also saw a major mountain building phase, known as the Taconic Orogeny, which formed a volcanic island arc along the eastern coast of Laurentia, a forerunner to the later Appalachian Mountains. The climate of the Ordovician was generally warm and humid, what scientists call a greenhouse Earth. Global sea levels were much higher than they are today, and vast, shallow seas covered large parts of the continents. This created a perfect environment for marine life to flourish. The oceans were teeming with life, and scientists often refer to this time as the Great Ordovician Biodiversification Event. This was a major boom in life. The number of marine families more than tripled, rising from about 160 at the start of the period to more than 400 by the end. The diversity of marine life grew in both the number of species and the complexity of their ecosystems. While the Cambrian was the dawn of animal diversity, the Ordovician was when many of the basic animal groups really became numerous and widespread. Brachiopods, trilobites, and graptolites were especially abundant. Bryozoans, crinoids, cephalopods, and jawless fish also thrived. Life on land also began to appear for the first time. The oldest fossils of land-based plants were found from this period. They were small, moss-like plants that lived in damp environments. Fungi also made their appearance on land, forming the very first soils. However, the Ordovician did not end peacefully. The period concluded with a devastating mass extinction, the second largest in Earth's history, known as the Late Ordovician Mass Extinction, or the Ordovician-Silurian Extinction Event. It happened around 443.8 million years ago and wiped out over 85% of all marine species. This event was primarily caused by a severe global ice age, the Hernantian glaciation, which was triggered by a dramatic drop in atmospheric carbon dioxide and a change in ocean circulation. As glaciers formed and grew on Gondwana, global sea levels dropped sharply, destroying the vast, shallow marine habitats where most life lived. This extinction set the stage for the Silurian period, which began around 443.8 million years ago and lasted for about 29.6 million years, ending around 419.2 million years ago. The name Silurian comes from the Silurian, another Celtic tribe that once lived in Wales, and was also coined by Roderick Murchison in the year 1839. The Silurian was a time of recovery and new beginnings. Life bounced back from the great extinction that ended the Ordovician, and new kinds of creatures appeared. The planet's climate began to stabilize and warm again after the icy extremes of the previous period. The glaciers melted, causing global sea levels to rise and flood the continents, a fact that geologists can read in the rock layers of this time. During the Silurian, the continents Avalonia, Baltica, and Laurentia continued their slow journey toward each other, eventually colliding to form a new supercontinent called Euramerica, or Laurussia. This monumental collision, known as the Caledonian Orogeny, created a vast mountain range that stretched from modern-day North America, across Greenland, and all the way to Norway. As these mountains formed, they began to erode, leaving behind salty basins and evaporate deposits, especially in regions like what is now Michigan and West Virginia. Life in the oceans recovered and diversified. The seas were ruled by enormous eurypterids, also known as sea scorpions, some of which grew to several meters in length. The first bony fish, or osteichthyons, appeared, and fish, in general, became more diverse, developing jaws that could move, a major evolutionary leap. Brachiopods, corals, and trilobites, though hit hard by the extinction, adapted and flourished again. This was also the golden age of mysterious, tube-shaped sea creatures called tentaculitoids. On land, The Silurian was a time of quiet revolution. For the first time in Earth's history, large fossils of land-based life appeared. Small, moss-like plants formed the first primitive forests along lakes and streams. Even more importantly, the very first vascular plants, plants with internal systems for carrying water and nutrients, appeared. The earliest known example, Cooksonia, was a tiny plant that grew along the water's edge, a precursor to all land plants that would follow. The Silurian also saw the first clear evidence of terrestrial animals. Fossils from around 425 million years ago show millipedes and spider-like creatures, suggesting that simple food chains were already beginning to form on land. Despite its reputation as a time of calm warmth, the Silurian climate was surprisingly unstable, with many dramatic climate shifts and smaller extinction events. Scientists have named several of these events, such as the Iriveccan, Molde, and Low events, all of which were marked by sudden sea level changes and a drop in biodiversity, especially for creatures that lived in the open water. We stand now at the summit of a great intellectual mountain. The long, arduous climb, which began with a simple observation of a map and led through decades of doubt, ridicule, and painstaking discovery, is over. The theory of plate tectonics is our reward. It is the master key to our planet's past, its present, and its future. We now understand that the ground beneath our feet is not solid and permanent, but a mosaic of immense rigid plates drifting upon the slow, fiery currents of the mantle below. We know that these plates are born in fire at mid-ocean ridges, and they die in fire at deep subduction zones. We know that in their grand, silent, and unending dance, they carry the continents with them. With this extraordinary power of understanding, we are no longer limited to simply observing the present. We can now become geological chrononauts. We can use the precise, mathematical laws of plate motion to reverse the tape of history. We can command the Atlantic to close, watch the Americas nestle back against the shores of Africa and Europe, and see the world of Pangaea reappear from the mists of time. But even this, the reconstruction of Pangaea, is not the beginning of the story. The history of our planet is far grander, more ancient, and more cyclical than that. Pangaea, for all its magnificent scale, was not a unique event. It was but one chapter in a much larger epic. Earth scientists now understand that the assembling and dispersing of supercontinents is a recurring theme in our planet's life story, a colossal rhythm that beats over vast eons of time. This is the supercontinent cycle. Imagine, if you will, the continents adrift on the mantle, like great wooden rafts on a thick, viscous sea. As they drift, they eventually begin to converge. Subduction zones form, ancient oceans are swallowed, and one by one, the continents collide, welding themselves together into a single, immense landmass, a supercontinent. But the very existence of this supercontinent sows the seeds of its own destruction. This colossal blanket of continental crust acts as a thermal insulator, trapping the immense heat escaping from the Earth's core. The mantle beneath the supercontinent begins to overheat, to swell upwards. The pressure builds over tens of millions of years, until finally, the great landmass begins to stretch, to crack, and to rift apart. New oceans are born in the fissures, and the fragments, our familiar continents, begin to drift away from each other once more, scattering across the globe, only to begin, eventually, the slow process of reassembly on the other side of the planet. This cycle, this planetary pulse of assembly and dispersal, is thought to take somewhere between 300 and 500 million years. Pangaea is simply the most recent iteration. Before Pangaea, there were other giants. Geologists have found faint, ghostly traces of these lost worlds in the ancient rocks. There was likely a supercontinent named Pannotia, which existed around 600 million years ago, and before that, an even grander and more long-lived supercontinent named Rodinia, which dominated the globe over 1 billion years ago. Pangaea's story is therefore not just the story of one landmass, but the story of the last time our planet's continents came together in their majestic cyclical dance. To truly witness the birth of Pangaea, we must rewind the clock much further back. We must travel to a time long before its formation, to a world that would be utterly alien to our eyes. Let us set our temporal sights on the early Paleozoic era, roughly 550 million years ago, during the Cambrian period, a time of explosive evolution in the seas. What did the world look like then? It was a world of many continents and vast oceans. There was no Pangea. The future continents were scattered across the globe like a broken puzzle. The largest and most significant player on this planetary stage was a true behemoth of a continent, a landmass already far larger than any single continent today. This was the great southern supercontinent of Gondwana. It was a colossal raft containing the geological cores of what would one day become South America, Africa, Arabia, Madagascar, India, Australia, and Antarctica. In this ancient time, this giant landmass was centered over the South Pole, and much of it was covered in ice. Floating alone, like great islands in a global sea, were the other major players. There was Laurentia, a large continent that comprised the ancient heart of North America, along with Greenland and parts of Scotland. Laurentia was a tropical landmass at this time, sitting astride the equator, its shores bathed in warm, shallow seas, teeming with the strange early life of the Cambrian explosion. To its east, across a widening ocean, sat Baltica, the geological core of Scandinavia and Eastern Europe, and further still, the continent of Siberia, which was also a lone landmass, rotated almost 90 degrees from its present orientation. And between these great landmasses were smaller, but no less important, pieces of the puzzle. There were microcontinents, fragments of crust that had broken off larger landmasses, such as Avalonia, a sliver of land that would one day become England, Wales, and parts of eastern North America. And there were volcanic island arcs, long, curved chains of volcanoes, much like modern Japan, born from subduction in the middle of the ocean. These continents were separated by vast, now vanished oceans. The most important of these, for our story, was the great Iapetus Ocean, which separated Laurentia from Baltica and Gondwana. The Iapetus was the precursor to the Atlantic, a wide and ancient body of water to the west of Laurentia, and encompassing most of the rest of the planet was the enormous Panthalassic Ocean, the super ocean that would one day become the Pacific. This was our stage, a world of scattered lands and wide, open seas. The assembly of Pangea is the story of how these oceans closed and how these separate lands were brought together in a series of titanic, slow-motion collisions, each one lasting for tens of millions of years. Each collision, which geologists call an orogeny, threw up mountain ranges that would have dwarfed anything we know today. The first great movements in this tectonic ballet began in the north. The Iapetus Ocean, which had been widening, began to close. A subduction zone formed along its edge, and the ocean floor of the Iapetus began to slowly sink back into the mantle. Laurentia, Baltica, and the island arc of Avalonia were now on a collision course. The first to arrive was Avalonia, around 480 million years ago. This microcontinent, a sliver of crust that had originally broken away from the northern edge of Gondwana, slammed into the coast of Baltica. But the main event was yet to come. The floor of the Iapetus continued to subduct, pulling the larger continents of Laurentia and the newly amalgamated Baltica Avalonia towards each other. The collision, when it happened around 420 million years ago, was an event of unimaginable scale and violence. It was not a sudden crash, but a slow, grinding, inexorable crunch that lasted for over 20 million years. As Baltica and Avalonia collided with the eastern coast of Laurentia, the edges of the continents, which had once been placid coastal plains, were now subjected to incomprehensible stress. The rock layers buckled, folded, and fractured. They were pushed up, one on top of another, creating immense sheets of rock called naps. The pressure was so intense, and the heat so great, that the very nature of the rock was changed. Sandstones were transformed into glittering quartzites, and shales were metamorphosed into gleaming schists and sturdy gneisses. Deep beneath the surface, the immense heat melted parts of the crust, creating vast subterranean chambers of magma that slowly cooled to form massive intrusions of granite. The surface expression of all this geological violence was a mountain range, a colossal mountain range. This was the Caledonian orogeny, and the mountains it created, the Caledonian Mountains, were likely among the grandest the planet has ever seen. We must not picture the worn-down, gentle hills we see today in Scotland or Norway. We must imagine a range of jagged, ice-capped peaks soaring to heights of 25 or even 30,000 feet, rivaling, or perhaps even exceeding, the modern Himalayas. This great chain of mountains, glowing red and orange under the ancient sun, stretched for thousands of miles, forming the backbone of a newly forged continent. The northern Apetus Ocean was gone, and in its place stood a single, unified northern landmass, sometimes called Euramerica, or the Old Red Sandstone Continent, after the distinctive red sediments that washed down from its mighty, eroding peaks. The first major piece of Pangaea had been assembled, but the world was still divided. To the south lay the still separate giant of Gondwana, between the new continent of Euramerica and the southern behemoth of Gondwana lay another ocean, known as the Reich Ocean. For a time, this ocean widened, but the engine of plate tectonics is relentless. New subduction zones formed, and soon, the Reich Ocean too began to close. Gondwana, the great southern landmass, began a slow, majestic northward drift, heading for a final, world-altering collision with Euramerica. This was to be the main event, the grand finale, the collision that would weld the northern and southern halves of the world together and truly form the core of Pangaea. This was not a single clean event, but a complex series of collisions that unfolded over nearly 100 million years, from about 380 to 280 million years ago. Geologists call this vast and protracted mountain-building event the Variscan orogeny in Europe and the Alleghenian orogeny in North America, but it was all part of the same colossal crunch. Imagine the northwestern coast of what is now Africa, slowly, centimeter by centimeter, bearing down on the southeastern coast of what is now North America. The floor of the Reiki Ocean was consumed beneath the continental margins, pulling the two land masses together. As they met, the initial contact was likely a soft, shearing collision, with parts of Gondwana grinding sideways along the edge of Euramerica, but eventually, the full force of the continental masses was brought to bear. The geological violence was even greater than that of the Caledonian orogeny. The continental margins, laden with thick layers of sediment washed into the Reich Ocean over millions of years, were now caught in a tectonic vice. These sediments were scraped off the descending plate, folded, faulted, and thrust upwards into a new, even more magnificent mountain range. This was the central Pangaean Mountains, the great suture that stitched the northern and southern continents together. At its zenith, this mountain range was a spectacle to rival any in Earth's history. It was a continuous belt of towering, alpine-style peaks that stretched for more than 5,000 miles. From what is now Mexico, the mountains ran through the southern United States, across the now closed Atlantic to northwestern Africa, and through Spain, France, and Germany into Central Europe. They were the heart of Pangaea, a vast, high-altitude barrier that would have a profound and devastating impact on the climate of the new supercontinent. Today, after 300 million years of relentless erosion by wind, water, and ice, only the deep, gnarled roots of this once mighty range remain. In North America, they are the familiar gentle folds of the Appalachian Mountains. In Europe, they are the scattered uplands of the Variscan Belt, the rolling hills of Brittany in France, the Black Forest in Germany, the plateaus of the Czech Republic. When we walk through these ancient, worn-down mountains today, we are walking through the very core of a collision that forged a supercontinent. We are treading on the remnants of peaks that once pierced the sky at Himalayan heights. But Pangaea was still not quite complete. While Euramerica and Gondwana had been welded together to form the main body of the supercontinent, another large continent, Siberia, still lay separate to the east. Between Siberia and the eastern margin of Euramerica, the part we know as Baltica, lay yet another ocean basin, but this too was destined to close. As the main Pangaean assembly was concluding, Siberia began to rotate and pivot, closing this final ocean. Sometime around 290 million years ago, it collided with Baltica. This final collision created the last great mountain range of Pangaea, the Ural Mountains. The Urals, which today form the traditional boundary between Europe and Asia, are the eastern seam of Pangaea. They are the suture line, where the last major independent continent was welded into the whole. And with that final weld, the work was done. The assembly was complete, around 250 million years ago, at the boundary between the Permian and Triassic periods. For the first time in over 500 million years, nearly all of the Earth's continental crust was gathered together into a single, magnificent, and monstrous landmass. The Iapetus was gone. The Reich Ocean was gone. The oceans that had once separated Siberia were gone. Pangaea was born. It stretched from the South Pole nearly to the North Pole, a giant C-shaped landmass cupped around the eastern Tethys Sea. The rest of the planet was covered by the single, world-spanning ocean of Panthalassa. The collisions had ceased. The mountain ranges stood at their zenith, jagged and immense. The Earth had been reshaped. The stage was now set for the next act in our planet's drama. But what kind of world was this? What would it have been like to stand on the surface of this new unified land? With the birth of Pangaea came the birth of a new and extreme global environment, a world of vast deserts, monstrous monsoons, and profound climatic challenges that would shape the destiny of all life on Earth. We must now leave the story of Pangaea's violent formation and step onto the soil of the supercontinent itself to explore the world that it created. The Carboniferous period was a time of dramatic transformation on Earth, lasting from about 359 to 299 million years ago. Its name, meaning coal-bearing, points to the most significant event of this era, the widespread formation of vast coal deposits. But the Carboniferous was about more than just coal. It was a period of high oxygen levels, a global ice age, and a major burst of life on land and in the sea. This period is often divided into two epochs: the Mississippian, early Carboniferous, and the Pennsylvanian, late Carboniferous. This was a time when the Earth's geography changed dramatically. The supercontinent Gondwana was still dominant in the south, while other landmasses, including Laurussia, a continent formed from the collision of Laurussia and Baltica, began to draw closer. These continental movements culminated in the formation of the ultimate supercontinent, Pangaea, at the end of the Carboniferous and into the Permian. This assembly created the central Punjab Mountains and caused a shift in global climate and ocean currents, coal swamps, and atmospheric oxygen. Most of the world's coal was formed during the late Carboniferous, a result of unique conditions that led to the burial of immense quantities of plant matter. Swamps and wetlands were the dominant ecosystems, particularly in the low-lying equatorial regions of Laurussia. Here, colossal lycopod trees, such as lepidodendron and sigillaria, along with giant horsetails and ferns, thrived in the hot, humid climate. These plants had evolved to produce a tough, woody substance called lignin, which resists decay. According to a key theory known as the delayed fungal evolution hypothesis, the fungi that could break down lignin had not yet fully evolved. This meant that when plants died, they didn't fully rot away. Instead, they accumulated in soggy, oxygen-poor swamps, forming thick layers of a spongy material called peat. Over millions of years, as these layers were buried under heavy sediment from rising sea levels, the pressure and heat transformed the peat into the dense, energy-rich rock we know as coal. This massive burial of carbon had a profound effect on Earth's atmosphere. By pulling vast amounts of carbon dioxide out of the air and locking it away in the ground, it caused a major increase in atmospheric oxygen levels. Gas bubbles, trapped in ancient salt crystals, and other geological records suggest that oxygen levels reached peaks of 25% to 30%, far higher than today's 21%. This oxygen-rich atmosphere is believed to have played a crucial role in supporting the giant arthropods that defined this period, such as the enormous millipede like Arthropleura and the colossal Meganeura a dragonfly-like insect with a wingspan of up to 75 centimeters. The late Paleozoic Ice Age. Despite the rise in global temperatures, at the very beginning of the period, the Carboniferous was dominated by a long and intense ice age. The late Paleozoic Ice Age. This was the most severe and prolonged ice age of the last 540 million years, triggered by the drawdown of atmospheric carbon dioxide, the formation and erosion of the central Pangaean Mountains, coupled with the widespread burial of organic matter in coal swamps, removed a significant amount of CO2 from the air, causing global temperatures to plummet. This cold period was marked by repeated cycles of glaciation as temperatures dropped. Massive ice sheets, some up to 30 in number, spread across the supercontinent Gondwana, covering parts of what are now South America, Africa, Australia, and India. As glaciers grew and shrank, sea levels repeatedly fell and rose, a cyclical process that is clearly recorded in the rock layers. This cycle of glacial advance and retreat shaped the landscape and led to the formation of alternating beds of carbonate and siliclastic sediments, a process known as cyclothems. This fluctuating climate, with periods of warming and cooling, had a major impact on life. The Carboniferous rainforest collapse, for instance, was a severe ecological event linked to a drop in atmospheric CO2 and a shift to a cooler, drier climate. The vast tropical forests that dominated the land broke apart into isolated patches, making it difficult for amphibians that relied on a moist environment to survive. Rise of reptiles and amphibians. While the Carboniferous is famous for its giant insects, it was also a critical period for the evolution of vertebrates on land. Amphibians were the dominant land animals. Having evolved from lobe-finned fish in the Devonian, they grew to impressive sizes, with some reaching lengths of up to 6 meters. Many were labyrinthodonts, a group with complex tooth structures and weak limbs, suggesting they were semi-aquatic. However, the late Carboniferous saw the rise of a new group of vertebrates, the amniotes. These animals, including early reptiles and synapsids, mammal-like reptiles, had a key evolutionary advantage: the amniotic egg. This hard-shelled egg could be laid on dry land, freeing amniotes from a reliance on water for reproduction. This allowed them to thrive in the increasingly arid conditions that emerged toward the end of the Carboniferous and during the Permian. As the climate dried out, amphibians declined, and reptiles began to diversify and spread rapidly. The first known reptile, Hylonomus, appeared at this time, along with Archaeotheris, the first synapsid. The Permian period. The Permian period, the final chapter of the Paleozoic era, lasted from about 299 to 252 million years ago. It was a time of continued continental collision, extreme climate, and the final rise of the animals that would rule the subsequent Mesozoic era. Pangaea and extreme climates. The Permian was defined by the existence of the supercontinent Pangaea, which had fully formed by the beginning of the period. This single, massive landmass created a unique and often harsh global climate. The interior of Pangaea was far from the moderating influence of the ocean, leading to vast, dry deserts and extreme seasonal temperature swings. Evaporite deposits and red-colored sandstones are common in rocks from this era, providing clear evidence of the arid conditions. At the start of the Permian, the late Paleozoic Ice Age continued, with glaciers still covering parts of Gondwana. However, the climate gradually warmed as the period progressed. The end of the Permian saw the highest temperatures in Earth's history to date, culminating in the Permian Triassic thermal event caused by massive volcanic eruptions in Siberia. The rise of synapsids. The Permian is often called the Age of Synapsids. This group of animals, which includes the ancestors of mammals, became the dominant land vertebrates of the period. Early on, primitive synapsids, known as pelycosaurs, thrived, including the famous sail-backed Dimetrodon. These creatures had already evolved more advanced features, like differentiated teeth and improved temperature regulation, making them well suited to the harsh climates of Pangaea. By the Middle Permian, the pelycosaurs were largely replaced by more advanced synapsids, called therapsids. These mammal-like reptiles were incredibly diverse and included saber-toothed predators like gorgonopsians and giant plant eaters like Dinogorgon. The first cynodonts, the direct ancestors of mammals, also appeared and began to spread across the globe in the late Permian. Simultaneously, the sauropsids, the group that includes reptiles, began to evolve. While they remained in smaller ecological roles for much of the Permian, the archosauromorphs, distant relatives of crocodiles and dinosaurs, made their first appearance at the very end of the period, setting the stage for the next era, the Great Dying. The Permian period came to a cataclysmic end with the Permian-Triassic extinction event, also known as the Great Dying. This was the most severe mass extinction in Earth's history, wiping out an estimated 96% of all marine species and 70% of land vertebrate species. The cause is strongly linked to massive volcanic eruptions in Siberia, which created the Siberian traps. These eruptions released enormous amounts of greenhouse gases, particularly carbon dioxide, which triggered a domino effect of environmental collapse. Global temperatures soared, oceans became acidic and oxygen poor, and ecosystems, both on land and in the sea, were devastated. The Permian-Triassic boundary marks the end of the Paleozoic era and the beginning of the Mesozoic. It was a blank slate for the next era of life, a world that would eventually be dominated by the archosaurs that survived this ultimate catastrophe, the golden age of dinosaurs. Look around you, my little guide chirps, her feathered body flitting from branch to branch. This is our world now. It is the age of my family. The Triassic-Jurassic extinction event had cleared the stage, and the dinosaurs, which had been small and a minor part of the ecosystem, exploded in size and diversity. The Jurassic was the golden age of the sauropods, the long-necked, plant-eating giants. Animals like Brachiosaurus, Diplodocus, and Apatosaurus became the largest land animals to have ever existed. They roamed the land in enormous herds, a testament to the abundance of plant life. To hunt these behemoths, a new kind of predator evolved. The theropods, bipedal carnivorous dinosaurs, became the top predators. The famous Allosaurus, a powerful hunter with rows of sharp teeth, was a common sight, as was the smaller and more agile Compsognathus. Even the skies were conquered by reptiles. My little feathered friend, the Archaeopteryx, was one of a group of feathered dinosaurs that would eventually give rise to all modern birds. It wasn't just my family in the skies, she says. Gliding to a halt on a moss-covered rock, the pterosaurs ruled the air. They weren't dinosaurs, but they were a spectacle to behold. The Jurassic skies were filled with these magnificent flying reptiles, from the small, agile Anorognathus to the much larger Rhamphorhynchus. They hunted fish, insects, and smaller reptiles, a dominant force in the skies for millions of years. The Jurassic was also an important time for marine life. The plesiosaurs and ichthyosaurs of the Triassic became the rulers of the seas, hunting fish and other marine reptiles. The first crocodiles appeared, but unlike their terrestrial Triassic relatives, they were well adapted for an aquatic lifestyle. A world of change. The Jurassic was a time of immense change, both geologically and biologically. The breakup of Pangaea changed ocean currents and weather patterns, leading to a new, lush world dominated by ferns, cycads, and conifers. On this new world, dinosaurs reigned supreme, but the seeds of the next great evolution had already been planted. Tiny, mouse-like mammals survived in the shadows, waiting for their turn to emerge. The Triassic period, which began around 252 million years ago, was the beginning of a new chapter in Earth's story. It was the first act of the Mesozoic era, or the Age of Reptiles, and the seventh geological period of the Phanerozoic Eon, the Age of Visible Life. The Triassic gets its name from the Latin word trias, meaning trias, because of the three distinct rock layers: a lower layer of red beds, a middle layer of marine limestone, and an upper layer of black shales that were found in Germany. The Triassic was a world of survivors and newcomers, still recovering from the catastrophic Permian-Triassic extinction event. the largest extinction in Earth's history. This period was bookended by two devastating mass extinctions, one at the beginning and another at the end, that profoundly shaped the course of evolution. A world of extreme climates. The Triassic climate was one of extremes. The continents were still fused into the single supercontinent Pangaea, which stretched from pole to pole. This massive landmass created a harsh continental climate with scorching hot summers and freezing cold winters. The vast interior of Pangaea was a dry, arid desert with red-colored sandstones and evaporite deposits serving as a fossil record of its dry conditions. While the poles weren't covered in ice, they were moist and temperate, a stark contrast to the dry center of the supercontinent. The immense size of Pangaea also created powerful mega-monsoon weather systems that swept across the continent, shaping landscapes and ecosystems. The start of the Triassic was one of the hottest times in Earth's history, a result of the enormous Siberian traps, volcanic eruptions, at the end of the Permian. This intense heat, known as the Permian-Triassic thermal maximum, was punctuated by a few shorter, cooler periods. However, the heat was temporary. The end of the Triassic, around 201 million years ago, was marked by another extreme heat wave, the end Triassic thermal event, which was caused by volcanic eruptions from the Central Atlantic magmatic province. This event triggered the Triassic-Jurassic extinction event, a crisis that paved the way for dinosaurs to dominate in the next period. Life on land and sea. In the aftermath of the Great Dying, life on Earth began to rebound. At first, the flora was dominated by simple, fast-growing plants like Pleuramea, a kind of ancient lycopod. But as the climate stabilized, new plant groups took over. The Benetalas, a group of seed plants that looked a bit like modern cycads, became widespread, along with ginkgos and conifers. Interestingly, there is a mysterious gap in the fossil record of coal, known as the early Triassic coal gap, suggesting that the swampy ecosystems needed for coal formation had not yet recovered from the extinction. On land, the Triassic was an age of a great takeover. Surviving amphibians, like the giant temnospondyls, bounced back, but the true rulers of the land were a new group of reptiles, the archosauromorphs. This group included the ancestors of dinosaurs, crocodiles, and birds. While the first dinosaurs appeared in the late Triassic, they were not yet the dominant animals. The real rulers were the pseudocians, or false crocodiles, a group of crocodile-like archosaurs that came in a dazzling variety of forms, from armored plant eaters to huge, two-legged predators. Meanwhile, the therapsids, the mammal-like reptiles that had dominated the Permian, declined, while some, like the pig-like Dicynodonts, experienced a brief comeback. They were gradually pushed into smaller ecological roles by the archosaurs. But this struggle led to a crucial evolutionary development. Some advanced therapsids, the cynodonts, evolved into the first mammals. These tiny, shrew-like creatures were forced to live in the shadows, leading to adaptations like fur, a higher metabolism, and a nocturnal lifestyle, traits that would prove essential for their long-term survival. In the oceans, life also recovered. The ammonites, shelled relatives of squid and octopuses, flourished, and new kinds of marine reptiles appeared. The ichthyosaurs, which resembled modern dolphins, evolved in the early Triassic and grew to enormous sizes. The sauropterygians, which included long-necked reptiles like Tanystropheus, also became common, along with the first plesiosaurs. The Jurassic period, the age of dinosaurs. The Jurassic period began around 201 million years ago and lasted until about 143 million years ago. It was the second and middle act of the Mesozoic era, and it is most famous for the spectacular rise of the dinosaurs. As we step into this new world, our guide will be an Archaeopteryx, a feathered dinosaur that bridges the gap between dinosaurs and birds. My little Archaeopteryx friend has seen it all. She's seen the world change, the old rulers fall, and a new dynasty rise from the ashes. She's here to show us the world she lives in, a world of giant trees and even larger creatures. Welcome to the Jurassic, she chirps, her small tooth beak opening as if in a smile. Continental drift and climate. The Jurassic was a time of continued continental drift. The supercontinent, Pangaea, had begun to break apart, a process that created new coastlines and inland seas and a global sea level rise. As the continents separated, the vast, dry deserts of the Triassic began to shrink, replaced by lush, green landscapes. The climate was generally warm and humid, with no evidence of polar ice caps. This created ideal conditions for plant growth, particularly for the enormous forests of conifers, cycads, and ginkgos. The oceans, however, faced challenges. Around 183 million years ago, a massive volcanic event caused the torsion oceanic anoxic event, which drained the oceans of oxygen and led to widespread extinctions among marine life. Our journey through Earth's ancient history now reaches its final act, the Cretaceous period. It began around 145 million years ago, following the Jurassic period, and ended abruptly about 66 million years ago. This was the third and final chapter of the Mesozoic era, the so-called Age of Reptiles, and the ninth and final period of the Phanerozoic Eon. The name Cretaceous comes from the Latin word creta, meaning chalk, because of the vast chalk deposits from this period found in Europe and the United Kingdom, particularly in the famous White Cliffs of Dover. The Cretaceous was a time of both peak diversity and ultimate catastrophe. It was a world of high sea levels, lush plant life, and the largest land animals to ever exist. But it all came to a fiery end in one of the most famous extinction events in Earth's history: continental drift and global climate. The Cretaceous was a period of intense continental drift. The supercontinent Pangaea continued to break apart, forming the continents and oceans we know today. The Atlantic Ocean widened, India separated from Africa and Australia, and the continents began to drift toward their current positions. This geological activity was also marked by volcanic eruptions that created immense volcanic plateaus, such as the Deccan Traps in what is now India. The global climate of the Cretaceous was generally warm and humid, what scientists call a greenhouse world. There were no polar ice caps, and sea levels were extremely high. Shallow, warm seas flooded the continents, creating vast inland seas like the Western Interior Seaway that split North America in two. The high sea levels also created more coastlines, fostering marine life and contributing to the formation of those famous chalk deposits from the shells of tiny marine organisms. A world of giant dinosaurs. This is the very end of my family's rule. Our little Archaeopteryx guide whispers, landing on a branch of a flowering plant. The big ones, my cousins, have never been larger. The dinosaurs reached their maximum size and diversity during the Cretaceous. The long-necked sauropods continued to evolve, and some, like Argentinosaurus and Patagotitan, grew to immense sizes, weighing more than 70 tons. The ferocious, two-legged theropods also reached their peak, with iconic predators like Tyrannosaurus Rex ruling the land. These top predators were now armed with huge, bone-crushing jaws and powerful legs. But the Cretaceous was also a time of innovation. New kinds of dinosaurs emerged, including armored dinosaurs, like Ankylosaurus, and horned dinosaurs, like Triceratops, which defended themselves with massive bony frills and sharp horns. New groups of flying reptiles, the pterosaurs, also appeared, including the immense Quetzalcoatlus, a creature with a wingspan of over 10 meters, making it the largest flying animal of all time. In the seas, new kinds of marine reptiles evolved to hunt in the vast oceans. The mosasaurs, powerful swimming lizards, became the dominant marine predators, replacing the ichthyosaurs and plesiosaurs of the Jurassic. Sharks and bony fish, including the ancestors of modern fish, also became more diverse and abundant. The rise of flowering plants and insects, perhaps the most significant evolutionary event of the Cretaceous, was the rapid rise of flowering plants, or angiosperms. While they first appeared in the early Cretaceous, they quickly diversified and spread across the globe. This was a revolutionary development. Unlike older plant groups, like conifers and cycads, which relied on wind for pollination. Flowering plants used colors, scents, and nectar to attract insects and other animals to help them reproduce. This coevolution between flowering plants and insects led to an explosion in new species. As a result, insects like bees and butterflies, which co-evolved with flowers, became far more diverse. We saw the world change right before our eyes, our guide says, from a world of green and brown to a world of endless color. It was beautiful, but also a sign of things to come. The emergence of flowering plants created new food sources and habitats, supporting the evolution of new kinds of herbivorous dinosaurs and the small mammals that were still living in the shadows. The Cretaceous Paleogene extinction event, our little guide says, her voice suddenly somber, and our ending was a fiery one. The Cretaceous period came to a devastating close around 66 million years ago with the Cretaceous Paleogene (KPG) extinction event. This was a catastrophic global disaster that wiped out an estimated 75% of all species on Earth, including all non-avian dinosaurs. The cause is now widely believed to be a massive asteroid impact. The evidence points to the Chicxulub impactor, a space rock approximately 10 kilometers wide that struck the Earth near the Yucatan Peninsula in Mexico. The impact would have released more energy than 1 billion atomic bombs, creating a huge crater, triggering tsunamis, and sending an immense cloud of dust and debris into the atmosphere. This dust cloud would have blocked out the sun, plunging the world into months or even years of darkness and extreme cold, a period known as impact winter. The resulting collapse of photosynthesis caused food chains to unravel from the bottom up. Large animals, including all the dinosaurs, pterosaurs, and marine reptiles, were hit hardest, but some life forms survived, especially those that were small, lived in fresh water or underground, and could live on a varied diet. Among the survivors were birds descendants of dinosaurs, like our guide, crocodiles, turtles, and most importantly, the mammals. The extinction event was a complete reset for life on Earth. The disappearance of the dinosaurs cleared the way for a new group of animals to take control. The little mammals, who had survived in the shadows for over 100 million years, now had a world of empty ecological niches to fill. This marked the end of the Mesozoic era and the beginning of the Cenozoic era, the age of mammals, and a new story of evolution and adaptation that would eventually lead to us. The formation of Pangaea was not a single, dramatic event, but the result of the Earth's slow, constant movement over hundreds of millions of years. The planet's crust is broken into massive tectonic plates that glide over the softer material beneath, a process measured in mere centimeters per year. This gradual motion, however, is powerful enough to reshape the entire face of the planet. Long before Pangaea, there were other supercontinents, like Rodinia and Pannotia. They came together, broke apart, and their pieces drifted across the globe in a repeating cycle of assembly and separation that geologists call the supercontinent cycle. These fragments of land, including Laurussia, the future North America, and parts of Europe, Gondwana, which would become South America, Africa, Antarctica, Australia, and India, and smaller pieces, like Siberia, were on a slow collision course. As these land masses drew closer, the oceans between them began to shrink. The Rike Ocean, for instance, which once lay between Laurussia and Gondwana, vanished entirely, crushed out of existence by the merging continents. This was not a gentle process. When land meets land, the collision is violent. Rock crumples under immense pressure, and entire mountain ranges rise where plates lock together. The Appalachian Mountains in North America and parts of the Atlas Mountains in Africa are silent relics of these ancient impacts, the very scars that stitched Pangaea together. A planet of extremes. The unification of the continents created a new kind of world, one with a climate unlike anything seen today, with a single vast landmass and no inland seas to carry moisture. The climate was defined by its extremes. Far from the moderating influence of the ocean, Pangaea's core became a continental heartland, so isolated that rain rarely fell. This gave rise to enormous deserts that may have stretched for thousands of kilometers, a stark contrast to the humid, forested coastal regions. The coasts, bathed in moisture from the surrounding Panthalassa Ocean, were a different world. Here, dense forests of primitive trees, seed ferns, and towering conifers flourished, feeding on heavy rains carried inland. These were the humid, carboniferous forests, whose decaying plants would eventually form the coal seams we still mine today. The air was rich in oxygen, making it possible for some insects to grow to remarkable sizes, such as dragonflies, with wings nearly a meter across, and giant, millipede-like creatures. The enormous size of Pangaea also created unique, global wind systems, without the complex shapes of modern continents to break their flow. Winds could sweep across thousands of kilometers with little interruption. This meant that dust from the vast interior deserts could travel immense distances, carried by winds to distant coastal forests. Conversely, rainfall struggled to reach the heart of the continent, making Pangaea a world of extremes, where hot, arid zones gave way to cooler, humid coastal regions. Life in a unified world. Perhaps the most striking result of Pangaea's formation was its influence on the evolution of life. By uniting all the continents, Pangaea erased the barriers that had once separated ecosystems. This meant that species that had evolved in isolation suddenly came into contact with one another. Animals and plants could now spread freely across the entire landmass, creating ecosystems that spanned much of the supercontinent. Fossils from this time prove this. Identical species of reptiles and plants have been found on continents now separated by entire oceans, showing that during the age of Pangaea, the same species walked across lands that are today thousands of kilometers apart. Early reptiles adapted to survive in the dry heat of the interior, while early amphibians followed rivers that acted as highways, connecting different regions. The diverse landscapes of Pangaea, from its deserts and grasslands to its lush coastal forests, became a crucible of evolution, shaping the ancestors of creatures that would one day dominate the planet, including dinosaurs and early mammals. Though Pangaea was unified, it was never permanent. The same restless forces that built it were already at work, preparing to tear it apart again. But while it lasted, it left an extraordinary mark, shaping the evolution of life and carving out the deep foundations of the world we know today. Look at our world, a familiar sphere of deep, abyssal blue and vibrant, sprawling green and brown. 6 distinct continents, adrift in the silent, patient expanse of 5 great oceans. This is the Earth we know, the planet we have mapped and measured and memorized since our very first glance at a globe or an atlas. It is the foundation of our geography, the stage upon which all of human history has unfolded. But this arrangement, this seemingly permanent configuration of land and water, is merely a snapshot, a fleeting moment in the incomprehensibly vast timeline of our planet's existence. The Earth, you see, is not a static object. It is a living, breathing, and endlessly dynamic entity. For 4.5 billion years, it has been in a constant state of transformation, a cosmic sculptor, forever reshaping its own surface. There have been epochs buried deep in time when the planet was a sphere of ice, a snowball hurtling through space, its continents groaning under the weight of glaciers miles thick. And there have been other eras, equally alien to us, where the poles were lush and green, free of any ice, and the oceans swelled to levels we can scarcely imagine. In this grand planetary ballet, the most dramatic performers have always been the continents themselves. These colossal rafts of rock are not fixed in place. They are wanderers, drifting across the face of the deep, driven by forces that originate in the very heart of the world. They have collided with unimaginable force, thrusting jagged mountain ranges towards the heavens. They have rifted apart, creating new oceans in the process, and sometimes, in rare and momentous periods of geologic history, they have come together. Imagine a world without the Atlantic Ocean, a world where you could, in theory, walk from the shores of what is now North America directly into the lands of what is now Europe and Africa. Imagine a world with no Indian Ocean, no Pacific separating Asia from the Americas, Imagine all the lands, all the continents we know today, and some that have long since vanished, gathered together into a single, colossal landmass, a true supercontinent. This world is not a fantasy. It was real, about 335 million years ago. This is precisely what the Earth looked like. This singular continent, a gargantuan puzzle of assembled landmasses, has been given a name by scientists, a name that perfectly encapsulates its magnificent scale. They called it Pangaea. The name is derived from ancient Greek pan, meaning all, and Gaia, or G, meaning earth or land. Pangaea, all earth. For a time, it was nearly all the earth that was land, concentrated in one hemisphere, and surrounding this immense continent was a single, planet-spanning ocean, an equally super ocean, named Panthalassa, meaning all sea. This was a different planet. The climate was a thing of extremes, unlike anything in our modern experience. The very air had a different composition, and the life that crawled and grew upon its surface was utterly alien. Vast deserts of red sand stretched for thousands of miles in its interior. Strange, resilient plants, precursors to the conifers we know today, clung to life in a world often starved of rain. And the animals, this was not yet the age of the dinosaurs. Not at first. It was an age of bizarre amphibians, some the size of crocodiles, and strange, mammal-like reptiles, who were the dominant terrestrial creatures on the planet. This was the world of Pangaea, a world that existed for over 100 million years, a world that looked as if it would exist forever. But the same titanic forces that brought it together would eventually tear it asunder. Around 200 million years ago, this mighty supercontinent began to crack, to fracture. Deep fissures, bleeding magma from the planet's molten heart tore through its crust. The land began to stretch and thin, and finally to break apart. The pieces, the continents we know today, began their long, slow drift away from each other, a process that continues to this very day. The Atlantic Ocean was born in the wound of its separation. The continents moved into the positions we find them in now, and in their wake, the world we recognize was born. To conceive of this, to imagine the sheer power required to push and pull entire continents across the globe, like pieces on a chessboard, is to grapple with a force and a time scale that dwarfs human comprehension. It is a story written, not in books, but in the very rocks beneath our feet, in the shape of our coastlines, the structure of our mountains, and the fossilized remains of creatures that lived and died on a world that no longer exists. This is the story we are going to explore. We will travel back in time to walk the strange landscapes of Pangaea. We will witness its birth, its life, and its violent, world-altering death. But first, we must ask a fundamental question. How do we know any of this? How did humanity first stumble upon the radical, almost unbelievable idea that the continents themselves could move? The journey to understanding Pangaea begins not with a satellite or a supercomputer, but with a simple map, and with the curious gaze of people who dared to notice something that was, in hindsight, hiding in plain sight. For centuries, as the age of exploration dawned and mapmakers began to chart the globe with increasing accuracy, a curious feature became apparent to anyone who studied the emerging picture of the world, a peculiar, almost deliberate symmetry. The great English philosopher and scientist Francis Bacon, as early as the year 1620, noted the uncanny parallelism between the western coast of Africa and the eastern coast of South America. It was more than a vague resemblance. It was a jigsaw puzzle fit. A bulge on one continent seemed to correspond perfectly to a bite on the other. It was an observation, an interesting little riddle, but nothing more. The technology and the scientific framework to explain it simply did not exist. Over the next 200 years, others would notice it as well. Thinkers and naturalists on both sides of the burgeoning Atlantic would comment on the strange congruence, but the prevailing view of the Earth was one of permanence. The continents and oceans were seen as primordial features, fixed in place since the planet's creation. The land might rise or fall slightly, mountains might be thrown up by catastrophic events or worn down by erosion, but the fundamental geography was static. To suggest otherwise was to venture into the realm of pure fantasy. The continents were made of solid granite, anchored deep into the planet's interior. The idea that they could somehow plow through the solid rock of the ocean floor was, quite simply, absurd. The intellectual dam began to show its first cracks in the mid-19th century. Scientists were uncovering a world far older and more dynamic than previously imagined. The fossil record was revealing a succession of strange life forms, of extinctions and creations that spoke of immense spans of time. Geologists studying rock strata were piecing together a history of dramatic environmental change. In this environment of burgeoning discovery, an Italian-American geographer named Antonio Snider Pellegrini, in the year 1858, did something remarkable. He not only noted the fit between Africa and South America, but he also pointed out that coal deposits in both Europe and North America shared identical fossilized plants. To explain this, he produced two maps. The first showed the Americas nestled snugly against Africa and Europe, forming a single landmass. The second showed the continents in their present positions, after having been torn apart by the biblical Great Flood. His mechanism was wrong, tied to religious catastrophe rather than scientific process, but the image he created, the image of the continents united, was a powerful and prophetic one. Yet, these were still just whispers, at the edge of mainstream science. The established geological community, particularly in Europe and North America, built its understanding on the theory of a cooling, contracting Earth. The planet, they believed, was like a drying apple. As its molten interior radiated heat into space and cooled, the entire globe shrank. This contraction caused the crust to wrinkle, and these wrinkles were the world's mountain ranges. The lower areas, the parts that sank, became the ocean basins. It was a neat, mechanical, and widely accepted model. It was also, as we now know, fundamentally wrong. The stage was set for a revolutionary, someone with the intellectual courage and interdisciplinary vision to connect the scattered clues, the puzzle piece coastlines, the matching fossils, the strange continuity of mountain ranges across vast oceans, into a single, cohesive, and earth-shattering theory. That person was not a geologist, which was perhaps the key to his insight. He was a German meteorologist, an Arctic explorer, and an astronomer. His name was Alfred Wegener. Alfred Wegener's journey began, as many great scientific leaps do, with a moment of simple observation. The story as told by Wegener himself is that the initial spark occurred around 1910. He was in his study, looking at a New World atlas, like Bacon and others before him. He was struck by the fit of the continents across the South Atlantic. But for Wegener, this was not just a casual curiosity. It was a question that lodged itself in his mind and refused to let go. He described it as an immediate impression, an idea that felt strangely compelling, even without proof. At first, he dismissed it as an improbable fancy. The idea was too radical, too contrary to everything he had been taught, but the seed had been planted. Then, in the autumn of 1911, a new piece of information fell into his hands that would change everything. He came across a scientific paper that summarized the paleontological evidence for a former land bridge between Brazil and Africa. The paper discussed the discovery of identical and very specific fossils of plants and animals on these two widely separated continents. The conventional explanation at the time was the existence of vast, sunken land bridges. It was proposed that massive continents had once existed in the oceans, a lost continent of Atlantis in the Atlantic, or Lemuria in the Indian Ocean, which had provided corridors for life to spread before conveniently sinking beneath the waves without a trace. Wegener found this explanation deeply unsatisfying. It seemed ad hoc, an invention designed to solve one problem while creating an even bigger one. Where did these immense landmasses go? There was no evidence for their sunken remains on the ocean floor. Wegener saw a much simpler, more elegant solution. A solution that didn't require inventing phantom continents. What if the lands themselves had been joined? What if Brazil and Africa were once part of the same landmass and had since drifted apart? For Wegener, It was a moment of profound revelation. He wrote to his future father-in-law, "If it turns out that sense and meaning are now becoming evident in the whole history of the Earth's development, why should we hesitate to toss the old views overboard?" He began to search, methodically, and with a passion bordering on obsession, for every piece of evidence he could find, from every scientific discipline he could access. He was a meteorologist, an expert on climate, but he dove headfirst into geology, paleontology, and geophysics. He was assembling the ammunition for an intellectual war. On January 6, 1912, at a meeting of the German Geological Association in Frankfurt, the 31-year-old Alfred Wegener stood before the assembled experts and presented his theory of continental displacement. He argued that the continents were not fixed. He proposed that they were rafts of lighter crust, which he called sile, floating on a denser, deeper layer, which he called sima, and he declared that in the late Paleozoic era, all of these continents had been grouped together into a single supercontinent. He called it, for the first time, Pangaea. The reaction was not just skeptical. It was hostile. It was scornful. The geologists in the audience saw Wegener as an outsider, a weatherman dabbling in a field he did not understand. Who was he to challenge a century of established geological doctrine? His ideas were dismissed as the delirious ravings of a madman. One prominent German geologist scoffed that his theories were nothing but moving crustal castles in the air. An American paleontologist called the theory utter damned rot. The criticism was often personal and vicious. He was accused of shoddy scholarship, of cherry-picking data, of being a dilettante. The core of the scientific objection, however, was not just professional jealousy or dogmatism. It was aimed at the greatest weakness in Wegener's argument, the mechanism. Wegener had presented a compelling case that the continents had drifted, but he could not provide a convincing explanation for how what conceivable force could be powerful enough to shove a landmass the size of South America across the planet. How could a continent made of relatively brittle granite plow its way through the dense, solid basalt of the ocean floor without shattering into a million pieces? The physics just didn't work. Wegener, in his desperation to provide a driving force, proposed two possibilities. The first was a force he called Pullflucht. The second was the tidal pull of the sun and the moon. He argued that over millions of years, these gentle gravitational tugs could have dragged the continents westward. His opponents, who were expert physicists, immediately tore these arguments to shreds. They demonstrated, with incontrovertible mathematics, that the forces Wegener proposed were many orders of magnitude too weak. The centrifugal force was negligible, and for the tidal forces to be strong enough to move continents, they would have to be so powerful that they would have stopped the Earth's rotation entirely within a few years. Wegener had built a beautiful case file, full of circumstantial evidence, but without a murder weapon, without a credible mechanism. The jury of the scientific establishment would not convict. His grand theory of continental drift was cast out, relegated to the fringes of respectable science, considered a cautionary tale of speculative excess. But Wegener was not a man easily dissuaded. Convinced of the fundamental truth of his vision, he did not surrender. He spent the rest of his life tirelessly gathering more data, refining his arguments, and publishing new editions of his landmark book, The Origin of Continents and Oceans. He knew that the evidence from the Earth itself was his greatest ally, and the most intuitive piece of evidence, the one that had started it all, was the geological and geographical fit. Let us return to that map, the one that so captivated Wegener. Let us look closer, with the eyes of a geologist. The fit between South America and Africa is not just a party trick, it is stunningly precise, especially if you look not at the modern coastlines, which are constantly being altered by erosion and changing sea levels, but at the true edge of the continents, the submerged continental shelves. In the early 1960s, long after Wegener's death, a British geophysicist named Edward Bullard used a computer, a new and powerful tool Wegener never had, To plot the fit of the continents at the 500-fathom line, the result was breathtaking. The overlap was almost non-existent. The continents locked together with a precision that defied coincidence. But the evidence goes far deeper than just the shape. Wegener pointed to the geology of the rocks themselves. He showed that ancient rock formations, known as cratons, which are the stable, primordial cores of continents, matched perfectly across the Atlantic. A specific 2-billion-year-old craton in West Africa, for instance, is truncated at the coast. It simply stops. Across the ocean, in Brazil, a craton of the exact same age and composition appears, as if it were the other half of a broken stone tablet. This was not a generic similarity. It was a precise match of rock type, age, and chemical signature. And then, there are the mountains. This was perhaps Wegener's most compelling geological argument. Mountain ranges are not random features. They are the scars of ancient continental collisions. Wegener demonstrated that if you reassembled the continents into Pangaea, several ancient mountain chains, now separated by thousands of miles of ocean, would snap back together into a single continuous belt. Consider the Appalachian Mountains of eastern North America. They are a familiar, ancient range, worn down by hundreds of millions of years of erosion. They run up the coast and disappear into the sea off the coast of Newfoundland, now travel across the Atlantic Ocean. In Ireland, in Scotland, and in Scandinavia, you will find mountains of the exact same age, with the exact same type of folded rock structures, and containing the exact same suite of minerals. These are the Caledonian Mountains. When the continents are reassembled in a Pangaea configuration, the Appalachians and the Caledonians link up perfectly. They become one single, magnificent mountain range, a range that marked a collision between ancient North America and ancient Europe long before the Atlantic Ocean ever existed. To the geologists of Wegener's day, this was a staggering coincidence. They were forced to argue that two identical mountain ranges, with identical histories, just happened to form on opposite sides of a vast ocean at the same time. Wegener's explanation was far more logical. They weren't two mountain ranges. They were one, a single range, a single scar that was later ripped in two when Pangaea fractured and the Atlantic was born. He found other, similar connections. A distinctive series of rock layers in South Africa, known as the Cape Fold Belt, terminates at the coast, across the water. In the vicinity of Buenos Aires in Argentina, an almost identical sequence of rocks appears, with the same folds and the same history. The evidence was everywhere he looked. It was as if he had found two halves of a torn newspaper, and could show that not only did the edges match, but the very lines of text ran continuously from one piece to the other. The physical land itself was telling a story of union and of violent separation. The shapes of the continents, the nature of their ancient rocks, the continuity of their long-dead mountains, all of this was powerful testimony. It was the first pillar of proof for the lost world of Pangaea. Yet this was only the beginning of the evidence. The silent stone spoke of ancient connections, but an even more powerful and evocative story was waiting to be told. A story told by the dead, by the fossilized remains of the plants and animals that had once lived and thrived upon this single, unified landmass, completely unaware of the oceans that would one day separate their graves. The story of life on Pangaea would provide the next crucial chapter in this scientific revolution, a line of evidence that was in many ways even harder to dismiss. The stones of the earth had begun to speak in the precise fit of the coastlines, in the ancient, shattered mountain chains. A story of a former union was being whispered. Alfred Wegener had assembled a powerful geological case, one that suggested the continents were not immutable fixtures of our world, but rather wandering fragments of a long-lost whole. His arguments were logical, they were elegant, and they were almost universally rejected. The wall of scientific orthodoxy stood firm, built upon the foundation of a static earth, and for every piece of geological evidence Wegener presented, his critics had a ready answer, a counter-theory that to them seemed far more plausible than his wild fantasy of drifting lands. But Wegener's case was far from complete. He had another line of evidence to present, one that was, in many ways, far more difficult to explain away. He turned from the inanimate testimony of the rocks to the animate and far more evocative testimony of the dead. The fossil record, a library of stone, holding the imprints of countless creatures and plants that had lived and died across the unimaginable expanse of geologic time. And within this library, Wegener found a mystery, a biological impossibility that demanded an explanation. Identical species of land-dwelling animals and stationary plants were being discovered on continents, now separated by thousands of miles of deep, unforgiving ocean. How could this be? How could a small, crawling reptile, built for life on solid ground, exist in both southern Africa and South America? How could a fern, with seeds too heavy to be carried by the wind for more than a few miles, have spread its progeny across India, Australia, Antarctica, and Africa? To the scientific establishment of the early 20th century, the answer was as colossal as it was convenient: land bridges. They envisioned that, in the distant past, immense continents had risen from the ocean floor, creating vast corridors between the lands we know today. Great isthmuses, like a prehistoric Panama, were thought to have stretched across the Atlantic and Indian Oceans, allowing life to migrate freely. And once their evolutionary purpose was served, these bridges, and indeed entire lost continents, like the fabled Atlantis or the theoretical Lemuria, had simply sunk, vanished, without a trace beneath the waves. The idea of Lemuria, for instance, was born from the curious distribution of lemurs and their kin found in Africa, Madagascar, and parts of India and Southeast Asia. To explain this, the English zoologist Philip Sclater, in the 1860s, proposed a triangular continent that once occupied the Indian Ocean, connecting these now distant lands. The great German biologist Ernst Haeckel even suggested that Lemuria was the likely cradle of humanity. It was a compelling idea, an epic of a lost world, and for a time, it was the only explanation that seemed to fit. It preserved the sanctity of fixed continents while accounting for the strange distribution of life. But Alfred Wegener looked at this theory with the critical eye of a physicist, and he saw that it was impossible. He knew from geodetic measurements that the crust of the continents was fundamentally different from the crust of the ocean floors. The continents were made of a lighter granitic rock he called sile. The ocean floor was made of a denser basaltic rock he called sima. For a land bridge, a continent, to sink, it would have to be forced down into a substance denser than itself. This violates the fundamental laws of buoyancy, the very principle of isostasy that keeps continents floating high upon the mantle. It is like expecting a great wooden ship to spontaneously sink to the bottom of a mercury sea. It simply does not happen. Furthermore, if these land bridges had existed and had subsequently foundered, where were their remains? The oceans are not bottomless pits. If a landmass the size of India had sunk in the Atlantic, its drowned mountains and plateaus should be detectable. But even the earliest, crudest oceanic soundings revealed no such thing. They showed deep, abyssal plains and a great mountain range running down the center of the Atlantic, but no sign whatsoever of sunken continents. The land bridge theory was a phantom, a ghost invented to solve one problem, only to create a far greater, physical one. Wegener proposed his simpler, more radical solution. There were no sunken bridges. There were no lost continents. The bridges had been the continents themselves. The reason the fossils matched up across the oceans was because at the time these creatures lived and died, there were no oceans between them. Let us now walk through this evidence, piece by piece. Let us meet these silent, fossilized witnesses that Wegener called to testify on behalf of his theory. Our first witness is a small, unassuming creature, but its testimony is among the most powerful. Its name is Mesosaurus. Imagine a reptile, perhaps 2 to 3 feet in length. It had a long, slender body, a flattened tail for propulsion, and jaws filled with a thicket of long, needle-like teeth, perfect for snatching small crustaceans and fish from the water. Its feet were webbed, its bones dense. It was an aquatic creature, but it was not a creature of the open ocean. Detailed analysis of the rock in which its fossils are found and the nature of its skeleton tell us that Mesosaurus lived in shallow coastal waters, brackish estuaries, and freshwater lakes. It was a creature of the shoreline, not the high seas. Now, consider where its fossils are found. They are discovered in only two places on the entire planet. One is in the Karoo Basin of South Africa. The other is in the Paraná Basin of Brazil and Uruguay. These two locations are separated today by nearly 3,000 miles of the South Atlantic Ocean, and the fossils are not just found generally on these continents. They are found in a narrow, specific band of rock strata from the early Permian period, about 290 million years ago. If you push the continents of South America and Africa together, these two narrow bands of Mesosaurus fossils line up perfectly. How could this be? Could this small, freshwater reptile have undertaken the Herculean task of swimming across a proto-Atlantic ocean? It is inconceivable. It would be like a freshwater perch deciding to swim from the coast of Ireland to Newfoundland. It would not survive the journey. It would perish from the salinity, the temperature, the sheer exhaustion, and even if, by some miracle, one did, could an entire breeding population have done so to establish themselves on a new continent and in precisely the same type of environment they left behind? The odds are astronomically against it. The land bridge theory also fails here. If a land bridge had stretched across the Atlantic, one would expect to find Mesosaurus fossils all along its length, and perhaps in other areas where the bridge made landfall, but they are found nowhere else. Only in this one specific, corresponding sliver of southern Africa and South America. Jenner's theory provides the only explanation that is both simple and profound. The reason Mesosaurus is found in these two places and nowhere else is that during the Permian period, these two places were one, they were part of the same lake district, the same system of river estuaries on the southern shores of Pangaea. The Mesosaurus didn't swim across an ocean, it simply swam from one side of a lake to the other. The ocean formed later, splitting its homeland and its graveyard in two. Let us call our next witness. This one is a more formidable creature, a powerful, land-dwelling predator of the early Triassic period, about 250 million years ago. Its name is Synignathus. Picture a creature, perhaps the size of a modern wolf. Its name means dog jaw, and for good reason. It had a large skull, powerful jaws, and differentiated teeth, with incisors at the front and shearing cheek teeth at the side. This was not a primitive reptile. It was a highly advanced synapsid, a mammal-like reptile that lies on the evolutionary line that would eventually lead to us. It was a fast, active predator, built for running down its prey on solid ground. It was, in every sense of the word, a terrestrial animal. The fossils of Synignathus are found in South Africa, and they are also found in South America. Once again, we are faced with an impossible journey, a wolf-sized, land-roving animal, somehow traversing thousands of miles of open ocean. The idea is patently absurd. No land bridge is needed to explain this. When Synignathus was alive, hunting its prey across the Triassic landscape, South Africa and South America were joined. The plains of the Karoo were contiguous with the pampas of Argentina. It was all one hunting ground. The parade of witnesses continues. Let us meet one of the most important of all, a creature whose discovery in the coldest, most remote place on Earth would, decades after Wegener's death, provide the final, stunning confirmation of his ideas. The creature is called Lystrosaurus. Lystrosaurus was a survivor. It lived through the Permian-Triassic extinction event, the greatest mass extinction the world has ever known, and in the aftermath, it became the most common terrestrial vertebrate on the planet. For a time, perhaps as many as 95% of all land animals were Lystrosaurus. It was a peculiar-looking herbivore, about the size of a pig. It had a stout, barrel-chested body and a strangely shaped skull. It had no teeth, save for two prominent tusks that grew down from its upper jaw, much like a walrus. It likely used these tusks for digging up roots and tubers. It was a slow-moving, land-dwelling, plant-eating animal. It was not a swimmer. It was not a traveler. Its fossils were first found in abundance in South Africa. Then they were found in India. Then in China. Already, the map of its distribution was posing a problem for the fixists, but the true revelation was yet to come. Decades passed, with Jenner's theory, while not forgotten, remained on the scientific fringe. Then came the 1960s, an era of new technology and new discoveries. In the Austral summer of 1969, a paleontologist named Edwin Colbert and his team were searching for fossils in the desolate, frozen landscape of the Transantarctic Mountains. In the frigid air, at an altitude of over 6,000 feet, they made a discovery that would send shockwaves through the world of geology. They found a piece of a jawbone, a fossil. It was a fragment of the skull of a Lystrosaurus. Antarctica, a continent of ice, locked at the bottom of the world, separated from Africa by the vast and stormy Southern Ocean. How did a pig-sized, land-dwelling reptile get there? The discovery was electrifying. There was no conceivable way for Lystrosaurus to have crossed the thousands of miles of ocean to reach Antarctica. It couldn't have swum. It couldn't have clung to a raft of vegetation for months on end. The only rational explanation was that Antarctica itself had moved. Colbert's discovery of Lystrosaurus in Antarctica was hailed as one of the most significant fossil finds of all time. It was the keystone that locked Wegener's arch of evidence into place. The only way to explain the distribution of Lystrosaurus in Africa, India, and now Antarctica was if these three continents were once huddled together in a single landmass, a great southern continent, which Wegener and others had called Gondwana, which itself was the southern portion of the greater supercontinent of Pangaea. The evidence from the animal kingdom was overwhelming, but the plants told the exact same story. Wegener's final star witness was not an animal, but a fossil fern, a plant known as Glossopteris. Glossopteris was a woody, seed-bearing plant, a dominant feature of the southern landscapes during the Permian period. It was not a towering tree, but it formed vast, dense thickets across the land. Its most distinctive feature was its tongue-shaped leaves, from which it gets its name, and crucially, it reproduced via seeds that were quite large and heavy. They were not seeds built for travel. They could not have been carried for thousands of miles by the wind. They could not have floated for years across saltwater oceans and remained viable. Yet the fossils of Glossopteris are found in one of the most widespread distributions imaginable. They are found in Australia, in Antarctica, in India, in southern Africa, and in South America. How could this single type of plant have colonized 5 continents, now separated by the world's greatest oceans? The land bridge theory collapses completely under this evidence. It would require a network of bridges connecting all of these southern continents into an impossibly complex web. And again, there is no evidence for such a network. Wegener took a map and he plotted the known locations of Glossopteris fossils. Then, he cut up the map and moved the continents. He tucked the subcontinent of India into the space between Africa and Antarctica. He nestled Australia against the eastern edge of the Antarctic coast. He closed the Atlantic, bringing South America back against Africa. When he did this, the scattered, impossibly widespread distribution of Glossopteris suddenly coalesced into a single, contiguous, and perfectly sensible province. The fern hadn't crossed any oceans. It had simply spread across a single, unified landmass, Pangaea. The fossil evidence was a narrative unto itself. It told a clear and consistent story, the story of a world without the oceans we know today, a world where animals could walk from Africa to Antarctica, where forests could stretch from Australia to India. It was a powerful and compelling case. But Wegener, the meteorologist, had one more card to play. He knew that the past was not only recorded in rocks and fossils, but also in the faint, lingering traces of ancient climates. He knew that the Earth's great climatic zones, the tropics, the temperate bands, the polar caps, are determined by the planet's rotation and its relationship to the sun. If the continents were fixed, then their climates, broadly speaking, should have been fixed as well. A continent near the equator should always have been tropical. A continent near the pole should always have been cold. But the geological record told a very different and very puzzling story. A story of climates gone haywire. A story of ice in the tropics and of lush tropical swamps in the Arctic. A paleoclimatic paradox. Consider the evidence for ancient ice ages. When a glacier, a vast river of ice, grinds its way across a landscape, it leaves behind unmistakable evidence. It deposits a unique, chaotic jumble of rocks and sediment known as till, and as it moves, the rocks embedded in its base cut deep, parallel grooves and scratches into the bedrock below. These are called glacial striations. They are the fingerprints of a glacier, and they show the precise direction of the ice's flow. During Wegener's time, geologists had found extensive evidence of a massive glaciation. During the late Carboniferous and early Permian periods, around 300 million years ago, they found thick layers of ancient, hardened till, called tillite, and they found bedrock covered in glacial striations. It was found in South America, in Southern Africa, in India, in Australia, all lands which today are largely temperate or tropical. How could there be continent-spanning glaciers in India, which now straddles the equator? Under the fixed continent theory, this would imply a global ice age of unimaginable severity, one that coated nearly the entire planet in a thick sheet of ice. But this was directly contradicted by other evidence from the very same time period. While these southern continents were apparently frozen solid, the northern continents were experiencing a warm, wet, tropical climate. In North America, in Europe, and in China, vast, steaming, tropical swamps covered the landscape. These swamps would later form the great coal deposits that fueled the Industrial Revolution. This was the paradox. How could you have glaciers in the Congo Basin while simultaneously having tropical rainforests in Pennsylvania and England? It made no sense. The climatic belts of the Earth seemed to be thrown into chaos. Alfred Wegener saw the solution with startling clarity. The problem wasn't that the Earth's climate was broken. The problem was that the map was wrong. He took his scissors and his glue pot to the map of the world once again. He reassembled the southern continents into the great landmass of Gondwana, the southern half of Pangaea. When he did this, the scattered evidence for glaciation suddenly snapped into focus. The glaciated areas of South America, Africa, India, Australia, and Antarctica all joined together, forming a single, coherent ice sheet centered neatly over the South Pole. The puzzle was solved. The glaciers hadn't formed in the tropics. The tropics had moved away from the glaciers. The land itself had drifted north, away from the pole, carrying the scars of its icy past with it. The glacial striations provided the final, elegant proof on a fixed map. The directions of ice flow, indicated by the scratches in the rock, were nonsensical. Glaciers in southern Africa seemed to have moved onto the land from the ocean, which is impossible. But on Wegener's Pangaean map, it all made sense. The striations all pointed outwards, away from the center of the great polar ice cap, showing the natural, radial flow of a continental glacier. It was a stunning vindication. And what of the coal deposits? The evidence for tropical swamps in the far north? Wegener's model explained this just as elegantly. He showed that during the Carboniferous period, those parts of North America and Europe that were covered in coal swamps were not in their present northern latitudes. On the Pangaean globe, they were located right on the equator. They were in the perfect position to host the lush, tropical vegetation that would one day become coal. They had since drifted north, carrying their tropical inheritance with them to their current, colder homes. The picture was now breathtakingly complete. The shapes of the continents fit together. The ancient rock formations and mountain ranges lined up. The fossil animals and plants showed a world without oceanic barriers, and the evidence of ancient climates, the ice and the coal, all fell perfectly into place on his new map. Wegener had presented a case built on a vast, interlocking web of evidence from a dozen different fields of science. He had shown that the Earth's past could only be understood if one accepted the mobility of the continents. The evidence was overwhelming. The logic was inescapable. And yet, for decades more, the scientific world refused to listen. They held fast to their static Earth, for despite the mountains of evidence that Jenner had piled up to show that the continents had moved, he still could not answer that one damning question that had haunted him from the very beginning. How? What force on Earth or in the heavens was powerful enough to accomplish such a feat? What titanic engine could drive entire continents across the face of the globe? This was the Achilles heel of his theory, and without a mechanism, his beautiful, elegant, and powerfully supported idea remained, in the eyes of most scientists, nothing more than a fascinating, but ultimately impossible, dream. The key to that final, crucial mystery lay hidden, buried, in the one place no one had yet been able to properly explore, the deep, dark, silent floor of the ocean. The journey through the age of the dinosaurs has been a complete one. We have traced their origins, explored their biological marvels, and witnessed the monumental events that brought their reign to a close. We have delved into the science of their discovery and the enduring mystery that surrounds them. The narrative, as presented in its multiple parts, has covered the entirety of this epic story. It has reached its logical and fulfilling conclusion, leaving no major chapter of the dinosaur saga untold. The final echoes of their story are not found in new text, but in the lessons we have learned about life, time, and the ever-changing nature of our planet. The case was closed, yet the verdict was not guilty. Alfred Wegener, the persistent meteorologist, had presented a mountain of evidence. He had connected the continents with the unerring lines of their coastlines, the strata of their ancient rocks, and the ghostly continuity of their shattered mountain ranges. He had called forth witnesses from the deep past, the fossilized remains of creatures and plants whose very existence on now distant shores defied all logic unless those shores were once united. He had solved the baffling paradox of ancient climates, explaining with breathtaking simplicity how glaciers could exist in the tropics and tropical swamps could thrive in the Arctic. He had, in essence, described the scene of the crime in meticulous detail. He had shown the world what happened, but he could not produce the culprit, the mechanism, the force, the great, earth-shattering engine that could drive continents across the globe remained a phantom, and without it, his grand, cohesive theory was dismissed by the mainstream of geology as a beautiful but impossible fantasy, a fairy tale, as one of his more charitable critics called it. And so, for decades, the idea of continental drift entered a long and lonely exile, following Wegener's tragic death on the ice sheets of Greenland in 1930. His theory lost its most passionate and tireless champion in the halls of academia, particularly in the geologically conservative institutions of North America. His ideas were not just debated, they were often ridiculed. They were held up as a cautionary tale, an example of speculative overreach, a warning to young geologists not to stray from the hard data of the rock hammer and the microscope into the dangerous wilderness of grand theory. The doctrine of permanence, of a static, solid Earth with continents and oceans fixed in place since primordial times, reasserted its dominance. The textbooks were written, and Wegener was largely written out of them. But an idea, this powerful, this elegant, this capable of explaining so much of the world's history, does not simply vanish. It may be driven underground, whispered only by a few dissenters, but it waits. It waits for new evidence, or for a new generation of thinkers willing to look at the old evidence with fresh eyes. And during these wilderness years, for continental drift, a few brilliant minds did indeed keep the flame of Wegener's revolution alive. One of the most important was a British geologist named Arthur Holmes. Holmes was a towering figure in the geology of the early 20th century. He was a pioneer in the use of radiometric dating to determine the age of rocks, effectively giving the Earth its proper, multi-billion-year-old birth certificate. Unlike so many of his contemporaries, Holmes was not dismissive of Wegener's work. He saw the profound explanatory power of a mobile Earth, and he understood that the single greatest obstacle was the lack of a plausible mechanism. While other geologists were scoffing, Holmes was thinking. As early as 1929, a year before Wegener's death, Arthur Holmes published a paper containing a truly revolutionary suggestion. He turned his attention away from the surface of the planet, away from the crust, and looked deeper into the vast, mysterious, and then unknowable region of the Earth's mantle. He proposed that the mantle was not a static, solid layer of rock. He suggested that, over immense geological timescales, it behaved like a fluid, a thick, viscous, incredibly slow-moving fluid. He reasoned that the mantle was being heated from below by the immense radioactive furnace of the Earth's core. This heat, he argued, would create colossal, slow-turning loops of circulation within the mantle, incredibly slow-moving, but incredibly powerful. He envisioned a process that we now see every day in a pot of simmering soup on a stove. Hotter, less dense material from the bottom rises. As it reaches the top, it spreads out, cools, and becomes denser. This denser material then sinks back down, only to be heated and rise again. Holmes proposed that these were the engines of the continents, these enormous, rotating systems of flow within the mantle, which he termed convection currents, would exert a powerful dragging force on the underside of the continental plates above. Where two currents were rising and diverging, they would stretch the crust, thin it, and ultimately rip it apart, creating new oceans and pushing the continents away from each other. Where the currents were converging and sinking, they would drag the continents together, causing them to collide and crumple up into great mountain ranges. It was the answer. It was the powerful, planet-scaled engine that Wegener had been missing. It explained how continents could be moved without having to plow through the solid ocean floor. Instead, the continents were simply passengers, carried passively on the back of this immense subterranean conveyor belt. But in 1929, this was a theory born almost entirely of logical intuition. There was no way to prove it. No one had ever seen the mantle. No one could drill deep enough to measure these supposed currents. Holmes's idea was brilliant, it was prescient, but it was untestable with the technology of the day. And so, while it was respected, it did not change the prevailing view. It remained a clever hypothesis, filed away in the scientific literature, waiting for its time. At the same time, in the southern hemisphere, a South African geologist named Alexander Dutoit was becoming Wegener's most devoted and important disciple. Dutoit was not a theorist like Holmes. He was a field geologist of extraordinary skill. He spent decades of his life trekking across the rugged landscapes of South America, Africa, India, and Australia, observing the rocks with his own eyes. He saw the evidence for Pangaea, not on a map, but etched into the very cliffs and valleys of the southern continents. Dutoit gathered a wealth of new, more detailed geological evidence that supported Wegener's original claims. He refined the picture, showing with even greater precision how the rock formations and ancient climates of these lands matched up. He became so convinced of the former unity of the southern lands that he championed the name Gondwana for this southern supercontinent, a name originally proposed by the Austrian geologist Eduard Suess. Dutoit went on to argue that Pangaea was not a single monolithic block, but was likely first composed of two great protocontinents, Gondwana in the south, and another landmass, Laurasia, in the north, which comprised ancient North America, Europe, and Asia. These two were separated by an ancient equatorial sea he called the Tethys. Due to its work was a monumental contribution. He added layers of detail and evidence that made the case for drift almost undeniable to anyone who studied the southern hemisphere. But even his immense body of field evidence could not overcome the stubborn skepticism of the northern hemisphere's geological community. The ghost of the mechanism problem still haunted the theory. And so, the impasse remained. The world plunged into the chaos of the Second World War, and questions of ancient geology seemed to fade into the background. Yet, it was this global conflict, and the long, tense Cold War that followed, that would paradoxically provide the very tools needed to unlock the planet's greatest secret. The next chapter in the story of Pangaea would not be written by geologists with rock hammers, but by naval officers with cutting-edge military technology. The focus of the search would shift from the familiar ground of the continents to the dark, unknown, and mysterious world of the ocean floor. For all of human history, the sea floor had been a realm of utter mystery. It was a blank space on our mental map of the world. We knew its surface, the shifting, restless waves, but the world beneath was a place of imagination, of krakens and sea serpents, of crushing pressures and eternal darkness. Scientists in the 19th century had assumed it was a cold, quiet, and profoundly boring place, a flat, featureless, abyssal plain, a dumping ground for the sediments that slowly washed off the continents over millions of years. They imagined it was an ancient, primordial landscape, largely unchanged since the Earth's formation. They could not have been more wrong. The key that unlocked the door to this hidden world was sound. During World War II, the terrifying effectiveness of the German U-boat fleet made understanding the submarine environment a matter of life and death for the Allied powers. They needed a way to detect submerged submarines and to navigate their own vessels safely through uncharted waters. The technology they perfected was the echo sounder, a system we now know universally as sonar. The principle was simple. A ship would send a pulse of sound, a ping, straight down into the water. This sound wave would travel to the seafloor, bounce off it, and return to a microphone on the ship's hull. By precisely measuring the time it took for the echo to return, and knowing the speed of sound in water, one could calculate the depth of the ocean at that point with remarkable accuracy. As a ship steamed along, it could send out a continuous series of pings, creating a continuous profile of the seabed topography beneath it. After the war, this military technology was released for scientific use. Oceanographic research vessels, crisscrossing the globe, began to map the ocean floor in earnest, and as the data poured in, a strange and utterly alien new world began to emerge from the darkness, a world that shattered every preconceived notion. The ocean floor was not flat. It was the most dynamic and dramatic landscape on the planet. The sonar charts revealed vast plains, yes, but they were cut by immense canyons and punctuated by thousands upon thousands of submerged volcanoes, which they called seamounts. Some of these seamounts had peculiar flat tops, as if their peaks had been sheared off. They were named guyouts, and their existence was a puzzle in itself. Even more stunning were the discoveries of colossal mountain ranges. These were not small hills, but ranges that dwarfed anything on land. The greatest of these was found to be a single, continuous, globe-circling system of mountains that snaked its way through all the world's oceans for a staggering length of over 40,000 miles. It was the planet seam. This was the mid-ocean ridge system, and running down the spine of this great global ridge, particularly in the Atlantic, was something even more remarkable. The charts revealed a deep, steep-walled valley, a great chasm, running right along the crest of the ridge, a rift. This is where our story narrows to focus on two remarkable individuals at Columbia University's Lamont Geological Observatory, Bruce Heezen and Marie Tharp. In the 1950s, Heezen was a senior scientist, leading expeditions to map the ocean floor. Marie Tharp was a geologist and draftsperson, working with the raw data that the research ships sent back. In that era, women were still barred from working on the oceanographic vessels, so while Heezen went to sea, Tharp stayed in the office, and it was she who had the monumental task of taking the endless columns of depth numbers and translating them into coherent profiles of the seafloor. As she meticulously plotted the data from the North Atlantic, point by point, sounding by sounding, she was the first human being to truly see the mid-Atlantic ridge in its full context. And she noticed something that no one else had. All of her profiles, taken from different ships over different years, showed the same feature, a deep V-shaped valley running right down the center of the ridge. It was persistent. It was real. She realized this must be a rift valley, a place where the Earth's crust was being pulled apart. She brought her discovery to Heezen. Heezen was a brilliant scientist, but he was a product of his time, steeped in the traditional, non-drift geology. His initial reaction was famously dismissive. He reportedly examined her work and told her it was just girl talk. The idea of a rift valley implied a pulling apart of the crust, a mobility that smacked of Wigener's discredited continental drift, a theory Heisen did not subscribe to. He, like many others, initially believed in an expanding Earth theory to explain the ridges, but Tharp was persistent. She knew what the data showed to bolster her case. She looked for an independent line of evidence. She got a map that plotted the epicenters of recent Atlantic earthquakes. She overlaid this earthquake map onto her map of the Mid-Atlantic Ridge. The result was a moment of pure scientific vindication. The earthquake epicenters fell perfectly within the boundaries of her rift valley. The earthquakes were happening inside the rift. This was not a dead ancient feature. This was a place where the earth was alive and actively tearing itself apart. When she showed this correlation to Heisen, he was stunned into silence. He could no longer dismiss her findings. This was undeniable proof. Together, they began a collaboration that would change the face of Earth science. Over the next few years, they synthesized all the available data into a single, spectacular, physiographic map of the entire ocean floor. Published in 1977, this map revealed the full, breathtaking majesty of the mid-ocean ridges, the deep ocean trenches, and the vast abyssal plains. For the first time, humanity could see the true face of our planet. The map was a masterpiece, a work of both science and art, and it hung on the wall of every geology department in the world. And at its heart was Marie Tharp's Rift Valley, the great scar where a new world was being born. The map showed what was on the ocean floor, but it did not, by itself, explain how it worked. That final, crucial leap of imagination would come from another veteran of the Second World War, a geologist and former submarine commander from Princeton University named Harry Hess. During the war, Hess had commanded an attack transport ship in the Pacific. He had left his vessel's echo sounder running continuously, a habit that annoyed the Navy but delighted the geologist in him. He had mapped thousands of miles of the Pacific floor, and he was haunted by its strange features, especially the mysterious, flat-topped guyotes. After the war, he pondered the new discoveries, the global ridge system, the deep trenches, the Rift Valley teeming with earthquakes. He also remembered Arthur Holmes's old neglected theory of mantle convection. In 1960, Hayes put all the pieces together in a paper he humbly called an essay in geopodetry. He laid out a theory of such elegance and power that it would become the very foundation of modern geology. He called it seafloor spreading. Hess proposed a beautifully simple model. The mid-ocean ridges, with their central rift valleys, were not wrinkles on a cooling planet. They were the sites where the great convection currents envisioned by Holmes were rising towards the surface. As the hot mantle material rose, it welled up into the rift, where it cooled, solidified, and formed fresh, new oceanic crust. This process, he argued, was continuous. It was like a factory, constantly manufacturing new seafloor. And as new material was added at the center, it pushed the older rock away from the ridge on both sides. The entire ocean floor, Hess proposed, was moving away from the ridge crest in two opposing directions, like a pair of giant conveyor belts. This was the master stroke. This was the mechanism. Wegener had been wrong in one crucial detail. He had envisioned the continents as ships plowing their way through the static, resistant ocean floor. This was the physical impossibility that had doomed his theory. Hess showed that this was not the case at all. The continents were not plowing through anything. They were passive passengers. They were being carried along, rafted on the back of the moving, spreading seafloor. The continents moved because the ocean floors moved. His theory also elegantly explained the other great mystery of the deep, the oceanic trenches. If new crust was constantly being created at the ridges, why wasn't the Earth expanding like a balloon? Hess proposed that there must be places where the old crust was destroyed. He identified these as the deep ocean trenches, the profound chasms that rimmed the Pacific Ocean. Here, he suggested, as the spreading seafloor reached the edge of a continent, it bent downwards and plunged back into the mantle, where it was remelted and recycled. He called this process subduction. It was a complete system, a global cycle of creation and destruction. Birth at the mid-ocean ridges, a long, slow journey across the ocean basin, and death in the fiery depths of a subduction zone. It explained the youth of the ocean floor. No rocks older than 200 million years had ever been found, because the older rock had all been recycled. It explained the guyots. They were volcanoes that formed at the ridge, had their tops eroded flat by waves at sea level, and were then carried away from the ridge, sinking into deeper water as they went. It explained everything. It provided the engine for Wegener's drift. Hess's seafloor spreading hypothesis was the long-awaited key. It connected the evidence from the continents with the new, dramatic evidence from the oceans. It provided the physical process that made continental drift not just possible, but inevitable. Yet, in the cautious world of science, even a theory as beautiful as this one requires definitive proof. Hess had proposed a model, a brilliant one, but it was still a hypothesis. How could you prove it? How could you demonstrate that the seafloor was truly moving like a conveyor belt? The answer, the final smoking gun, would not come from sound waves or rock hammers, but from the faint, invisible ghost of the Earth's ancient magnetism, a ghost that was frozen and recorded in the rocks of the ocean floor in a pattern so strange and so perfect, it would silence the remaining doubters once and for all. Harry Hess had offered the world a vision, a grand poetic concept of an ocean floor in constant motion, a planetary conveyor belt of creation and destruction that carried the continents as passive passengers upon its back. His hypothesis of seafloor spreading was the missing link, the elegant engine that Alfred Wegener's theory had so desperately needed. It was a beautiful idea. It connected the rising convection currents of Arthur Holmes's imagination with the stark, newly discovered topography of the mid-ocean ridges and the deep ocean trenches. It explained everything. And yet, in the rigorous world of science, elegance is not enough. A hypothesis, no matter how compelling, remains just a hypothesis until it is proven. It requires a prediction, a test, a piece of evidence so clear and unambiguous that it silences all doubt, a smoking gun. Hess had provided the theory, the how, but the world of geology, so deeply skeptical, after 50 years of dismissing Wegener, now demanded proof. That proof would not be found by drilling a hole to the mantle, or by measuring the movement of the continents in real time, a feat that was still technologically impossible. The final, definitive evidence for seafloor spreading, the discovery that would launch the theory of plate tectonics and complete Wegener's vindication, would come from an invisible force, a faint, ghostly presence that permeates our entire planet, a force that has been guiding travelers for centuries, but which holds a secret history of its own. It would come from the Earth's magnetic field. To understand this final, crucial chapter, we must first understand a property of our planet that is both familiar and deeply strange. The Earth itself is a magnet. Deep within its core, the churning motion of molten iron and nickel generates a powerful magnetic field, a dynamo of planetary scale. This field surrounds our world in a vast, invisible cocoon, the magnetosphere, which shields us from the harmful radiation of the sun. On the surface, we experience it most simply with a compass. A small, magnetized needle, free to pivot, will always align itself with the lines of magnetic force, pointing roughly towards the geographic poles. But this magnetic field is not just a navigational aid. It has the remarkable ability to become fossilized in rock. Many volcanic rocks, such as the dark, iron-rich basalt that makes up the entirety of the ocean floor, contain tiny microscopic crystals of magnetic minerals, most commonly a mineral called magnetite. When lava first erupts, either on land or from a deep-sea volcano, it is a molten fluid heated to over 1,000 degrees Celsius. At this extreme temperature, known as the Curie point, the individual magnetic domains within the magnetite crystals are agitated and free to move, like trillions upon trillions of microscopic compass needles floating in a liquid. They dutifully swing into alignment with the direction of the Earth's prevailing magnetic field at that moment. Then, as the lava cools and solidifies into hard rock, these tiny mineral compasses are frozen in place. Their magnetic orientation is locked in permanently. The rock itself has become a fossil compass, a silent, magnetic snapshot that preserves a precise record of which way was north at the exact time and place of its formation. This study of the Earth's ancient magnetism, locked away in its rocks, is called paleomagnetism. In the 1950s, long before the final seafloor mystery was solved, paleomagnetists began studying the magnetism of ancient lava flows on the continents, and they immediately ran into a series of profound puzzles. When they measured the magnetic orientation of rocks of different ages from the same continent, for instance North America, they found that the rocks did not all point to the current North Pole. In fact, rocks from 200 million years ago pointed to one position, rocks from 300 million years ago pointed to another, and rocks from 400 million years ago pointed to yet another. When they plotted these ancient pole positions on a map, it looked as if the Earth's magnetic North Pole had wandered or drifted all over the globe over geologic time. They called this phenomenon apparent polar wander, but this created an even deeper paradox. When their colleagues in Europe did the same thing, they also got a wandering path for the pole, but it was a different path. The North American path and the European path did not match. This was a physical impossibility. The Earth can only have one north magnetic pole at any given time. How could there be two different polar wander paths? For years, this was a major geological conundrum, but a few scientists, remembering Wegener, saw the beautifully simple answer. The pole had not wandered, the continents had. Imagine two people walking away from a single streetlight at night, each taking a different path from each person's perspective. It looks as if the streetlight is moving, and their perspective of the streetlight's apparent motion will be different. But if you know their starting point, you can reconstruct their paths and show that the streetlight never moved at all. The scientists realized it was the same for the continents. There was only one North Pole. The reason there were two different polar wander paths was that Europe and North America had once been together and had since drifted apart. When they took their maps and slid the continents back together, closing the Atlantic Ocean as Wegener had proposed, the two separate, nonsensical polar wander paths merged and became a single coherent path. It was a stunning, independent confirmation of continental drift. But this was not the strangest discovery to emerge from the study of fossil magnetism. As geologists examined long, layered sequences of volcanic rock on land, where lava flow had piled upon lava flow over millions of years, they found something that at first seemed to be an error in their equipment. Some layers showed a normal magnetic polarity, with the fossil compasses pointing towards today's north, but other layers, deeper down or higher up, showed a completely reversed polarity. The compasses within them pointed directly south. The finding was so bizarre that many were deeply skeptical, but as more and more data came in from different locations around the globe, the conclusion became inescapable. The Earth's magnetic field was not stable. Throughout its history, at irregular and unpredictable intervals, it had completely flipped. The North Magnetic Pole had become the South Magnetic Pole, and vice versa. A compass on the Earth, hundreds of millions of years ago, would have, at different times, pointed in opposite directions. This was a discovery of monumental importance. Using radiometric dating to determine the age of each lava layer, scientists could now build a precise timeline of these magnetic reversals. They could see that there were long periods of normal polarity, like the one we live in today, which they called crons, and these were punctuated by periods of reversed polarity. They began to build a reference, a barcode of geologic time, known as the magnetic polarity timescale. By the early 1960s, the history of these magnetic flips over the last few million years had been firmly established from rocks on land. And now, all the pieces were on the table. Harry Hess had proposed that the sea floor was spreading from the center, and on land, geologists had uncovered the wild history of the planet's magnetic reversals. The two ideas seemed completely unrelated, but it would take the insight of a few brilliant young minds to see that they were, in fact, two halves of the same perfect solution. At the same time these discoveries were being made, oceanographic ships were continuing their surveys, but now they were often towing new instruments behind them, magnetometers. These were highly sensitive devices that could measure the strength or intensity of the magnetic field emanating from the rocks of the ocean floor below. And when they plotted this data, another bizarre pattern emerged. The ocean floor's magnetism was not uniform. Instead, it was arranged in long, linear stripes running parallel to the mid-ocean ridges. Stripes of slightly higher than average magnetic intensity alternated with stripes of slightly lower than average intensity. More strangely still, this pattern was perfectly symmetrical on both sides of the ridge crest. If you found a wide stripe of high intensity, followed by a narrow stripe of low intensity, at a certain distance east of the ridge, you would find the exact same pattern, a mirror image, at the same distance west of the ridge. The ocean floor looked like a giant, stony zebra. No one had any plausible explanation for this perfectly regular, perfectly symmetrical pattern. The solution, when it came, was an act of pure scientific synthesis, a moment of genius that connected all these disparate threads of evidence into one unified theory. It came in 1963 from two researchers at Cambridge University, a 25-year-old PhD student named Fred Vine and his supervisor, Drummond Matthews. At almost exactly the same time, a Canadian geologist named Lawrence Morley independently came up with the identical idea, though his paper, in a now infamous decision, was rejected for publication as being too speculative. Their idea, which has come to be known as the Vine-Matthews-Morley hypothesis, was the smoking gun. It was the definitive proof of seafloor spreading. They started by accepting Harry Hess's idea as correct that new volcanic crust is continuously being created at the mid-ocean ridge and is then carried outwards in both directions. Then, they incorporated the second key idea that the Earth's magnetic field periodically reverses its polarity. They reasoned as follows. As hot magma rises and erupts at the mid-ocean ridge, it cools and solidifies. The magnetite crystals within it align with the Earth's magnetic field at that moment, locking in a record of its polarity. Let us say this happens during a period of normal polarity, like today. This newly formed strip of crust will be normally magnetized, and as it moves away from the ridge, it carries that magnetic signature with it. Sometime later, perhaps hundreds of thousands of years, the Earth's magnetic field reverses. The new magma now erupting at the ridge will cool and solidify in a world where north is south and south is north. It will become a strip of reversely magnetized crust. This new reverse strip then begins to move away from the ridge, pushing the older, normally magnetized strip ahead of it. Then the field flips back to normal. The next strip to form will be normally magnetized. Then it flips again, and the next strip is reversed. The result, they predicted, would be a perfect magnetic tape recording. The ocean floor itself was preserving the history of the Earth's magnetic reversals in a series of parallel, magnetized stripes. When a survey ship's magnetometer passed over a stripe of normally magnetized crust, whose magnetic field is aligned with the Earth's current field, the two fields would add together, producing a reading of slightly higher intensity. When it passed over a stripe of reversely magnetized crust, whose field opposes the Earth's current field, the fields would subtract, producing a reading of lower intensity. The zebra stripes were explained. They were not a feature of the rock itself, but a fossilized record of the planet's magnetic history, laid down on the spreading seafloor. The hypothesis also beautifully explained the symmetry. Since the seafloor spreads outwards from the ridge in both directions at the same rate, the pattern of stripes had to be a perfect mirror image on either side of the ridge crest. It was a breathtakingly elegant hypothesis, and better still, it made a clear and testable prediction. If the hypothesis was correct, then the pattern of wide and narrow magnetic stripes on the seafloor should exactly match the pattern of long and short magnetic reversal periods already known from the dated lava flows on land. The test came quickly. In the mid-60s, data from a U.S. Navy research vessel, the Eltonin, which had been surveying a section of the Pacific Antarctic Ridge, produced a spectacularly clear, high-resolution magnetic profile. It was a clean, unambiguous set of zebra stripes. Scientists took this seafloor magnetic profile and placed it alongside the magnetic polarity timescale that had been built from rocks on land. The match was perfect. It was absolute. The pattern of the stripes was identical to the pattern of the reversals. The wide stripes on the seafloor corresponded to the long periods of normal or reverse polarity, and the narrow stripes corresponded to the short, fleeting reversals. This was it. This was the proof. The ocean floors were moving. Harry Hess was right. Arthur Holmes was right. And the biggest vindication of all belonged to the man who had died on the ice 3 decades earlier. Alfred Wegener was right. The discovery published by Vine and his colleagues in 1963 unleashed a firestorm in the world of earth science. It was a revolution in the truest sense of the word. Within less than a decade, the entire foundation of geology was overturned. The old static models were thrown out. The fixists either converted, often with great enthusiasm, or they quietly retired. A new unifying theory rapidly took shape, incorporating continental drift, seafloor spreading, and the new knowledge of the Earth's structure. It was given a new name, plate tectonics. This new theory was more comprehensive than anything that had come before it. It stated that the Earth's rigid outer layer, called the lithosphere, which includes the crust and the very top, solid part of the mantle, is not a single, continuous shell like the skin of an apple. Instead, it is broken into a mosaic of about a dozen large, rigid plates and a number of smaller ones, all moving relative to each other. These plates are all floating on a hotter, softer, partially molten layer of the mantle beneath, called the asthenosphere, and the grand, slow dance of these plates explained everything. All of the Earth's major surface features and processes, earthquakes, volcanoes, mountain ranges, the very shape of the continents and oceans, were the result of what happens at the boundaries where these plates meet. Scientists identified 3 fundamental types of plate boundaries. First, there are the divergent boundaries. These are the places where plates are moving apart. The prime example is the mid-ocean ridge system, the creative seam of the planet, where new oceanic crust is being generated by seafloor, spreading, pushing the plates away from each other. This process is not just happening in the oceans. When this rifting process begins under a continent, it starts to tear the land apart, forming great rift valleys, like the modern East African Rift Valley, which is slowly, centimeter by centimeter, splitting the African continent in 2. The second type are the convergent boundaries, the destructive margins, where plates are moving towards each other. What happens here depends on the type of crust involved. When a dense oceanic plate collides with a lighter continental plate, the oceanic plate bends and plunges down into the mantle in a subduction zone. This process is incredibly violent. As the plate descends, it grinds against the overlying plate, causing the most powerful earthquakes on the planet. As it goes deeper, water baked into the oceanic crust is released, causing the overlying mantle to melt. This molten rock then rises to the surface to create chains of explosive volcanoes on the edge of the continent, like the great Andes Mountains of South America. If 2 oceanic plates collide, one will subduct beneath the other, forming a deep trench and a chain of volcanic islands, an island arc like Japan or the Aleutian Islands of Alaska. This is the reason for the Pacific Ring of Fire, a vast, horseshoe-shaped zone of intense earthquake and volcanic activity that traces the convergent boundaries of the mighty Pacific Plate. And finally, when 2 continental plates collide, the crust is too light and buoyant to subduct. Instead, the 2 land masses crumple, fold, and stack up on top of each other, creating immense, non-volcanic mountain ranges, like the towering Himalayas, which are the result of the Indian Plate crashing, and still crashing, into the Eurasian Plate. The third and final type of boundary is the transform boundary, where plates neither converge nor diverge, but instead slide horizontally past one another. The immense friction between the grinding plates means that the movement is not smooth. The plates lock together for long periods, building up incredible amounts of stress, which is then released in sudden, violent jerks, creating powerful earthquakes. The most famous example of a transformed boundary on Earth is the San Andreas Fault in California, which marks the line where the Pacific Plate is grinding northwestwards past the North American Plate. With these three boundary types, the theory of plate tectonics provided a single, elegant, unifying framework to understand the workings of our world. It was the geological equivalent of Darwin's theory of evolution or Einstein's theory of relativity. It was the paradigm shift that we Jenner had dreamed of. The revolution was complete. We finally understood the engine. We finally knew how the continents moved. And with this powerful new understanding, with this knowledge of the engine that drives the planet, scientists could now do something they had never been able to do before with confidence. They could rewind the tape. They could use the principles of plate tectonics to accurately reconstruct the past, to trace the long and epic journey of the continents. They could now begin to tell the full story, not just of Pangaea's existence and breakup, but of its very creation. The next chapter in our journey would be to travel back even further, to witness the slow, colossal, and majestic assembly of the greatest supercontinent the world had seen in an eon.